Good morning, Altspace. Can you do a sound check, please?
One, two, 1, 2.
This is for Altspace, Willie. Altspace. Sound check, please. Cannot hear you yet, Jay. Jay, I still cannot hear you. If you can do a sound check, that would be great. Still no sound, Jay. Yep, I hear you trying.
Test 1, 2.
I can hear you now, Jay, but it's a little low. Cannot hear you at all now.
Test.
Yes.
Test 1, 2, 3.
Perfect. That is
Okay.
a perfect volume.
Great.
Thank you so much.
Okay. Thanks.
I'm going to go ahead and mute you now. Hi, Simone. Are you ready?
Yes, hello, James. Good morning, everybody.
Okay, good morning, everyone. We're going to go ahead and get started. Welcome to day 4 of the Mars Society Convention. Our first 2 speakers today are mission support staff members from the Anomalies 20 Mars simulation. We have Dr. Simone Paternostro from Israel. He'll be speaking first, followed by Willibald Stumpner from Austria. Simone, take it away.
Thanks. Let me share the screen. Let me know if you can see it.
Yes.
Hello, good morning, everybody, or good afternoon, good evening. Here is 7 o'clock in the evening after one of the days of our mission here in Israel. So thanks for the presentation, James. My name is Simone Paternostro. In my daily life, I'm a space engineer. But in my free time, I support the Austrian Space Forum as a volunteer for their own projects and missions. But we will see a little bit more about the organization and what we are doing in the next slide. So first of all, the Austrian Space Forum is an organization mainly based on volunteers. It was founded in 1998. It involves more than 200 members that are international professionals and students in the space field, but not only from there, from multiple fields that can be STEM, psychological, business, and so on. And we focus on different area of expertise. In particular, the development of projects, and also in terms of hardware, physical hardware. We have developed the 2 Auda spacesuit simulator that we will see later on in another slide, but also in Mars analog rovers. So one of the main objectives of this organization is to perform research, so to broaden the knowledge of the international community related to the space field, in particular human exploration, and every consequences or side effect or any other aspects related, like planetary surface operations or even the optimization of remote site support. And in this research, we establish a lot of collaboration with other international partners to study human exploration in the different aspects. And one example is the mission that we are now performing this week's in Israel called Anomalies 20. But not only the research that is one of the main topics of the organization, is also spread the knowledge. So we are involved in a lot of educational and promotional activities, as you can see from the picture, with school and kids to promote the studies of STEM studies and to make people aware of what space is and what can bring to humanity. So as I mentioned, now we are in the Negev Desert in Israel. So the mission started on the 4th of October and will last until the end of October. And then we are the mission is in collaboration with the Israel Space Agency and is hosted by the DMARS. They are the organization that developed the station that we will see in the next slide. So the mission itself is a 3 weeks mission isolation, in which 6 analog astronauts will stay isolated in the station, performing different type of experiments. As I mentioned before, the habitat has been built by the DMARS team. They actually recently extended the station from a first module that they have until a few weeks ago, and now have two modules. And compared to our previous mission, usually our mission was formed by the analog astronauts and a support team, helping them in the setup of the station, performing the experiment, and a lot of other tasks. But in this case, the on-site support team instead has no direct contact with the analog astronauts, so they are, let's say, isolated from the contact point of view. Beside that, we have also a mission support center that is located in Austria, where there is another set of teams, actually quite bigger than the one we have in Israel, that support the whole teams here from remote. So they are kind of sort of Houston of the Austrian Space Forum. The mission itself has more than 20 experiments from different fields, from geology, psychological, microbiology, robotics, teleoperation as well. And all of this had involved more than 200 researchers from different countries. So like you can see more than 25 different countries. So here you can see just a few pictures coming from these days from the mission. There we have our analog astronauts inside the station, preparing for the EVA with our Auda spacesuit simulator. And on the right side of the slide, you can see our first full female crew going in EVA. And yeah, this is just a glimpse of what's going on, but you can find a lot of pictures and stories in the official media channels of the Austrian Space Forum. So this is the Auda spacesuit simulator. Is almost kind of unique. We are one of the few organizations worldwide that can that develop and operate this kind of technology. It's the suit itself, it weighs around 50 kilos. It's unpressurized. The upper part is a hard upper torso. It has a portable life support system with a custom built OBDH defined and developed by the organization itself, and also an advanced human machine interface. So the suit itself is designed to try to emulate the limitation, the sensorial limitation that a spacesuit would give to the astronauts. So from the limited vision to the tactile sensation. So the astronauts, they wear 3 different layers of gloves, and that this is really limiting the capabilities of handling tools and performing experiments. And so that's one of the objectives of the mission, is to try to figure out if the experiment, for how they are designed, they can be compatible for the way they can be operated by the astronauts. And beside that, there is also the astronauts. They are also wearing an internal exoskeleton that limits the movements of the main joints, like elbow, knees, and a little bit also the hands. So you can imagine that staying on EVA for between 4 and 8 hours. But in any case, wearing the suits for between 4 to 8 hours per day is quite exhausting, considering the weight and the whole limitation that the suits is imposing on the person. It's very challenging thing, but it's also very interesting and very particular sensation being inside. The suit itself, as I mentioned before, has a portable, let's say, life support system with different sensors that monitors the environment inside the suit and the health of the crew as well. And the telemetry itself is communicated to the base station here, and the other analog astronauts, they are inside the station, but also to the on-site support team and the team in Innsbruck. So there are multiple eyes checking on the crew health. This is only one of the missions that the Austrian Space Forum has performed so far. We have done 12 Mars simulation. Here you can see just the latest one from 2018 in Oman, and 2015 in a glacier in Austria, 2013 in the northern Sahara in Morocco, and then in 2012 again in Austria in the Caves. So all targeting a location that could resemble, for some features, a possible location on Mars, from the ice on one of the polar caps to the desertic environment, or even the caves that could be on Mars. So as I mentioned before, we had some slight differences for this mission, which we have the on-site support team a little bit, well, not a little bit, completely divided by the crew members inside the station, in order to increase the fidelity of what would be a possible scenario on Mars, where the astronauts would be completely isolated for any contact, personal contact outside themselves. And the experiment, as I mentioned before, they focus on multiple scientific aspects, from human factors to engineering, geology, biology, robotics. So it's very interesting. There are some experiments that are definitely interesting. It's worth to give a look, because okay, so there's another slide later on. I will tell you later that you can find all the information of our experiments on the website of the organization. This is what the more or less in a nutshell, the setup that we have for the missions. So we have the habitat that is performing the different experiment, and the results and all the information, the data is communicated to the to Earth, let's say, to our mission support center, that then forward all the information, the results and data to the different scientists, so the different experiment teams. The other peculiarity that we have in the mission is that the concept, we have a delay communication. So there is no real-time communication between the habitat and the mission support center. There is a delay. We have around 10 minutes delay, but it can be changed depending on the setup. But that's the standard. So whatever message or information or data is sent by the habitat or the mission support center to the other team, it's delayed in 10 minutes, creating a little bit of a challenge in the communication between the two teams, because for any issue or communication, you need to wait the answer. It's not going to be immediate, the answer from the other team. So I mentioned before, the mission support center in Innsbruck has multiple teams that support the mission itself, both in preparation but also in the real time. And it goes from the one that you can see in the picture, that's the flight control team, where we have then there are other teams that helps on a daily basis, and also in preparation of the mission, from the flight planning team, the ground support, the IT, the remote site support. So it's a very complex actually set up with multiple teams interacting to each other to define the mission and prepare for it. Plus all the external international communication with other teams, like here in Israel, we have the DMARS team that are supporting us with the setup. As I said before, if you're interested in the experiment and also the outcome of it, in the OVF, in the Austrian Space Forum website, you can find information for each mission in the Science Data Archive, with all the experiments that were performed and some of the data. And then you can even contact the OVF to get to know maybe the team behind the experiment, to get to know more, to get more information. And beside the whole mission itself, the Austrian Space Forum, we are also ourselves researcher or professionals or even students working on a project. So the outcome of this project always very often is published in journals or magazines and conferences. So this is one of the objectives I mentioned before: research and promoting what we are studying, and also to increase the common knowledge worldwide. And the other point is also try to promote itself from a media perspective, what we are doing, but in general the concept of human exploration, what is required in order to make more awareness, a general awareness. So we try to get media involved to promote what we are doing and spread the word, and allow more communities or group of people that would like to do the same to start their own setup, let's say, their own team. Well, actually, this was it. Then I don't know how you want to do. If you want to do a question at the end, and then we'll go for Willie at the moment next. Then we do a question at the end.
Yes, I think that would be the best. And by the way, my name is Lara, and I'll be asking questions on behalf of the audience. But I think we can go on and then do the Q&A later.
Perfect. Thank you very much, and thanks. Enjoy the rest of the day.
And by the way, if anybody has any questions, feel free to ask them in the Q&A panel, which is right next to the raise hand button. James, if you're here, are we ready for the next speaker, or should we wait a couple of minutes for the questions? And as we're waiting, we have one question from Stuart. Stuart is asking, do you have plans to extend the duration of the analog missions?
Sorry. Yeah, it was for some reason it was not able to mute myself. No, I mean itself, the mission is set. An extension would mean change a lot of the plan on many people because we are all volunteers. So most of us took days off and from work or from studies and so on. It would be difficult to extend suddenly in a mission. Everything is set up from the beginning to last at the exact time. Because we have to consider a lot of logistics in terms of the shipment of the material, also to take it back to Europe. So usually, yeah, when we finish the mission, then it starts the organization for the next one.
Thank you.
Lara, are there any more questions in the chat or the Q&A?
As for now, there are no questions, but as always, we do welcome them in the Q&A panel. And there is one question from the Outspace VR. Outspace VR, I'm handing it over to you.
Excellent. Are you able to hear us yet?
Yes, we do.
Are you? Fantastic. Thank you, Simone. I was curious. I know there's a lot of analog missions where we're testing the experience and the challenges. In your opinion, what do you imagine might be the greatest unmet need or thing that we're not yet testing with analog missions? The gap that we need to fill. What do you think is the thing we need to focus on?
Well, I'd say in terms of there are two sides from technological point of view, and the other one is from like more human perspective. I mean, if you think about it, even if we are in an analog simulation, we are still on Earth. So if anything happens, you're still not that far from civilization. So knowing that the closest point where other people are more than 6 months away of a flight, let's say from space, that might be the tricky part of psychologically speaking. So that might be one point that is still not well understood, how we would behave in that case, or if it can be done. And the other part is technological. I mean, being even NASA or ourselves, there are some parts that you cannot emulate. Like you can try to still pressurize the suit or pressurize the habitat, but you still are not in the same environment with no oxygen, very low atmosphere, radiation risk of micrometeorites and so on. So there is a lot of also technological speaking that it might be still to be fully understood on what we are able to. In particular, having an habitat so far away, then how you handle the maintenance of the habitat, how you like the concept of taking with you enough spare components, so you try to build them there. So all these challenges are really, really interesting, and I'm still working on it as far as I know.
Fantastic. Thank you.
Thanks to you.
And we got some more questions coming in from the Q&A panel. And next question is from Nicholas. Nicholas is saying, can you please describe some of the interpersonal experiments?
Interpersonal. Ooh, okay, then we have one experiment actually here that's called the Interteam, where you have a task. I haven't performed yet that experiment because it takes only few people from the on-site support team and from the habitat and from the mission support center, in which they have to perform a task almost simultaneously and then present each other the results. So I cannot answer more on what is the experiment itself asking during the questionnaire, because I haven't seen yet the questionnaire. But it's also an interesting concept, because then the two teams has to interact in some way. Considering we also are in time delay, then the outcome might be a bit different, or might be tricky to interact and to find. I think they have also to find each other question from some like, I don't know what to call them. It's a kind of mix between a game and psychological aspect. And inter-team, then you have also tele-operated robots. So there is some control from remote, can be from the OSS team, or even from the habitat itself. Yeah.
Just with the Q&A session.
And
No.
and sorry, then
We
any
presented
other question?
anyway.
I'm not sure
We
if
just
I
want to
answered
see
the question. If it's enough, or you want more clarification.
All right, thank you. Let's see. So we have a lot more questions coming in. Next question is from Michael. They ask, how do you account for the difference in gravity between Mars and Earth? In particular, the weight of the suit.
Yeah, so that's why the suit weighs 50 kilograms, because the current spacesuit used on the International Space Station, it's around 120 kilograms, as far as I remember. And considering the gravity on Mars, it's lower, then it's around more or less that weight. So we're talking about 45, 50 kilograms. So that's why it's 50, 45. So that would be, if the technology of the suit remain the same, then would means that whoever astronauts on Mars is wearing that kind of suit, it would wear 40, 45, 50 kilograms on himself.
Got it. Thank you. Next question is from Simon, and they say, a panel yesterday discussed promoting democracy on Mars. Can you field test do this somehow? Can your field test do this somehow?
Yeah, that's a very tricky question, because we have some chain of command here. So there is one in the crew, there is the team lead, the commander of the mission. Then the OSS team has the commander as well. Then in the mission support center is the flight director, and the chain of command is more or less that the flight director has the last, let's say, is the highest authority. So technically speaking, we have not exactly democracy. Probably it's just we have a team lead that is deciding in critical situations. But I think it might be, if any scientist is interested to see how it works, it might be even an option to give like the crew members to decide themselves, like vote for themselves or elect their own commander or whatever. It might be a good idea for an experiment, actually.
Thanks. Next question is from George. They say, your suit overlaps waist and shoes. Are these airtight?
No, as I mentioned before, it's not pressurized suit. So being a volunteer organization, we try to do our best, and having a pressurized suit means it's a lot of effort from a technological perspective, and that's something that the organization itself is not able. Mainly all these space agencies or even big companies like SpaceX might be able to do it.
All right. Next question comes from Dana. They say, do you train damage control procedures for Mars or Moon?
Damage control, let's say that since the station itself, sometimes it presents damages. Yes, actually it happens that we have anomalies with the equipment. Then there are procedure in place. So most of the procedure, especially for experimental equipment, they have some sort of troubleshooting activity. So you define some of common anomalies that might occur, and you put it down a procedure in order to say, okay, the astronaut has to follow this step to verify the cause of the issue and then try to solve it. But then the procedure cannot find the solution, let's say, then you put in contact with the mission support center and the specialist of that experiment, of that subsystem or equipment that you need, and trying to figure out what is the problem. Sometimes you need to repair it with they have some equipment inside from soldering or spare that can be used. But luckily, I mean, being here on Earth, if some big damage, it means that the equipment cannot be used. You can still replace it later on. So yeah, it's some sort of damage control, very minimal. It's troubleshooting as much as we can with the spare or the material that we have here.
Thanks. Next question from Jorge, and I'm sorry if I'm not pronouncing your name correctly. And they say, what about a pandemic in Mars? How to manage that?
That's another very interesting question. That's one of the points also to try to figure out in terms of resources you want to bring along. You want to bring all the medical equipment. So we're talking about from medicine to equipment that can be X-ray, MRI, or whatever. Then it would be interesting to understand how to handle this. Well, most of the astronauts usually they do, well, all the astronauts they do a quarantine before going on ISS. So they try to see if they develop any sort of like, let's say, quick disease in terms that shows symptoms quite quickly. But in some cases, it might be something in the long term, and then how much you can handle it. So how much equipment you want to bring with you. That's another big question, is the health of the astronauts. So how you handle this kind of emergencies or development of disease, or it could need special equipment that you don't have on there.
Thanks for the answer. And as we're getting closer to the end of this session, I want to ask you, what is the most innovative experiment or activity you are doing? It could be your personal opinion. If you could just elaborate on what are the most exciting, the things we should be on the lookout for, or some of the things that you've already done.
Okay, something here. We are doing mainly a lot of robotics. So we have also a couple of drones actually. So a quadcopter and the well, it is in the flying vehicle. I don't know how to actually. I'm missing one moment the word anyway. And ground robotics. So the idea of having,
they can hear us here.
Having a lot of support from rovers and drones, because the drones are expected to explore the area where the astronauts are supposed to go, in order to be sure that you are not going in a dangerous area because of, I don't know, from a geological perspective, or yeah, there are some ridges or canyons and so on that you want to avoid, or you want to explore a cave before they go there and then be sure that everything is safe. So telerobotics is I think is a very interesting concept to support future astronauts on Mars. And then also, I mentioned before, also the psychological aspect, I think, is a very important one. So to be sure that the astronauts are able to understand the group.
Can I ask about the materials used for different types of materials that's been used for the spacesuit? What materials are used, and go into detail of maybe the materials that are used to stitch them together, and how is it made together?
Well, the suit itself has 3 different layers. I think one, I don't remember all of them. One is Panox. The other 2 I have to check. I don't have it in my mind right now. But yeah,
it's a Kevlar-like material. It's a Kevlar-like material with a special surface treating to avoid backward and forward contamination. So it has a special kind of surface feature to minimize the contamination when you are exploring. And as Simone already said, one of the special features we are doing in the training is what we call the exploration cascade. We really start with orbiter pictures, deliberately not using the best we have on Earth, but simulating what we have for Mars. Then we send a flying drone there. Then we send a helicopter drone there. Then we send a rover there. All is part of this mission at the moment. And then we narrow down the point of interest. And then when we've chosen, then we send the astronauts there. And we have also some a movie prepared so you can see some of our astronauts in action if for the end of this presentation. And this especially is an all-female EVA, which might not have happened that often in previous analog missions.
All right, thank you very much, Simone and Willibald. The time is up, but
Yeah.
there are
If
still.
we could show like 30 seconds of movie as an end message, if you like.
That would be great. Absolutely,
One
yeah.
sec. Yeah. Just showing the video. So you see our two analog astronauts, Carmen and Annika, doing a night EVA. Also, you see them using a self-following robotic rover that they use also for carrying tools, samples, and things. So the human-robotic interaction is a big issue in our presentations, in our analog missions. So that's just a quick look at the end of our presentation. So you don't interact with our astronauts at the moment because they are already on time delay, but these pictures give you some idea of what they are currently doing in the Negev Desert. That would be all from our part. And as you can see, there is the Mission Support Center behind us, and a lot more rooms that look like this for all the teams.
Thanks a lot. This is very exciting. Thank you very much for the presentation. And as I said, there are some questions in the Q&A. So if you do have a little bit of time to look over them and answer by chat, that would be amazing. And we are
Would be our
ready.
pleasure. Yeah.
Wonderful. So our next speaker is Dr. Sarah Seeger from MIT with the presentation on biosignatures in Venusian atmosphere. Dr. Seeger, you're ready to start?
Hi, everyone. Good morning, good afternoon. I am here to tell you about the planet Venus. And 1 year ago, almost just over a year ago, I was part of a team that announced the detection of phosphine gas in the atmosphere of Venus. I'm going to come back and talk about that in a moment, but I'd like to start with the backstory. That starts a very long time ago, billions of years ago, when a simple, humble life form, cyanobacteria, figured out something very clever, how to harness energy from the environment, photosynthesis, and in the process gave off oxygen as a waste gas. And eventually, oxygen gas filled our Earth's atmosphere to 20% by volume. Now, oxygen is incredibly reactive, so it shouldn't be in our atmosphere at all. Without vegetation today and without photosynthetic bacteria, our atmosphere would have virtually no oxygen. What I like to think about is, mostly I work on exoplanets, but I like to imagine an intelligent alien civilization orbiting on a planet orbiting a nearby star with the kind of telescopes we're hoping to build. If they look at Earth, they'll know there's life here, or they'll suspect there's life here. And that's not from city lights or from things like the Great Wall of China, but it will be from oxygen gas. Now, as a scientist, I have this one quote I found some years ago that has really stayed with me and is one of my guiding principles. Nothing would be more tragic in the exploration of space than to encounter alien life and fail to recognize it. And why this weighs heavily on me is because, true, our Earth has oxygen, a fantastic biosignature gas, but our Earth has only had a significant amount of oxygen for 1 billion years. Now that sounds like a long time to a lot of people, but given that our Earth has been along much longer, I constantly think about, and my whole team is working on literally every single plausible gas that might be something we should think about that could be a biosignature gas on exoplanets. And while my team was working on this, we came across a really intriguing gas called phosphine, a phosphorus atom and 3 hydrogen atoms. Now on Earth, phosphine is only associated with life because, we have hardly any hydrogen on Earth. Phosphorus wants to go with oxygen atoms in the form of phosphate. And at the temperatures and pressures here on Earth, and even on the surface of Venus, it's just thermodynamically highly disfavored to make phosphine. Now, the discovery of phosphine on Venus is very controversial. It's not resolved yet. My team stands by the discovery. Other teams have looked at our data, analyzed our data, and have not found a signal. Other teams have reanalyzed the JCMT data and have seen a signal, but are pushing sulfur dioxide instead of phosphine. We stand by phosphine because if it was a sulfur dioxide line, we'd have to have way more sulfur dioxide than ever seen before. My talk isn't about phosphine, but I'll leave you with one more item on phosphine. And that is that Rakesh Moghul and team have been independently reanalyzing NASA Pioneer Venus data from nearly 4 decades ago, and they see signs of phosphine as well. So we're just going to have to let this play out. And in the meantime, I'm going to tell you about a bunch of other things. But first of all, Venus is actually a terrible place for life. We all know that the surface of Venus is so hot, hot enough to melt lead. You know, we were just hearing about Mars and Mars analog like Venus. We don't want to simulate the surface of Venus and ever imagine us humans going to the surface. And this is, of course, due to Venus's massive carbon dioxide atmosphere. But nonetheless, since Carl Sagan over half a century ago first put this idea forward, people have been speculating about the idea for life in the clouds, because about 50 kilometers above the surface, Venus is cool enough. Just like here on Earth and most planets, as you go above the surface, it gets colder and colder. And there's a layer in the clouds of Venus where the temperature is just right for life. And there's energy and there's liquid and there's other things that we all usually agree that life needs. Yet, even in the cloud layers, the clouds are incredibly acidic. They're made of concentrated hydrosulfuric acid that is way more acidic. Like, honestly, it's orders of magnitude more acidic than the most acidic environments we find life on Earth. And it's also very dry in the atmosphere, drier, 50 to 100 times drier than the driest place. So you might wonder why we're thinking about life on Venus, because it's so incredibly compelling. And Venus is not too far away. It's not too hard to get to. And so myself and a lot of others just want to sort of are actually reviving this idea that Venus could be an astrobiological target. So there's some new work I'll touch on. Some of it's published, some isn't. Jan Spacek and Steve Benner published a paper showing that if you start with a simple organic molecule, like perhaps formaldehyde that might come from meteorites, for example, in concentrated sulfuric acid, this small organic compound can react to produce a more complex organic set of chemistry, actually. And this is something people know about in industry, where they use concentrated sulfuric acid and their components they call red oil. This is the petrochemical industry. So in fact, there could be a lot of rich things happening in these sulfuric acid droplets, not necessarily related to life. The second topic I wanted to briefly mention is Daniel Dudovich at Harvard has been working in the lab, and he has shown, it's not published, but he's showing that certain lipids can self-assemble into a spherical shell in concentrated sulfuric acid. So if there is life in the clouds of Venus, in the droplets, perhaps it has an acid-resistant membrane. And third, what I'm going to talk about today may seem equally out there to you, but it's the idea of biological neutralization of these acid droplets to levels that are more acceptable for biological materials. So it turns out that here on Earth, there are actually examples of some life inside stomachs. You know, in your stomach, it's incredibly acidic. The acid breaks down food. And this life secretes ammonia, these microbes, to neutralize like a droplet-sized acidic environment. So I'm going to walk you through a sort of series of atmosphere anomalies, and then I'm going to, like at the big picture level, present a model that ties these together, that relies on life in the atmosphere. Okay, so just starting somewhere that people in the audience might be familiar with is this picture of Venus here. This is an ultraviolet image of Venus, and see those dark stripes? These are, we don't know what is causing these dark stripes specifically, what the composition of the so-called anomalous ultraviolet absorber is. But whatever these particles are, they are absorbing like 50% of all of the ultraviolet light that falls on the planet. So this is really intriguing. This isn't related to the theory I'm going to tell you about, but I just want to start out with this because it is something quite curious. So what I am going to do is show you a series of plots like this. This is showing you the altitude above the surface on the left side, on the y-axis in kilometers. On the right side, I'm showing you pressure in bar, and also it looks like temperature in Celsius. And these dots, they just represent clouds in the cloud layer of Venus. It's kind of just a cartoon, but I have some text here to go along with it. So another really intriguing, I'll call it anomaly or unexplained thing on Venus, is that in the lower cloud layers, there are larger particles that appear to be non-spherical. And why this is so intriguing is if it's not spherical, it can't be pure concentrated sulfuric acid. In fact, there has to be some more complex chemistry in the droplets. That, of course, doesn't mean there's life, but it's certainly intriguing and something that we'd like to be able to revisit on Venus. Okay, so interestingly, the Venera probes have seen quite a lot of phosphorus and iron detected in the cloud layers. And this is important because life, if it's there, it needs metals and other non-volatile elements for catalysis, at least life on Earth does. Now we come to a slightly more complicated situation that we do have a paper under review, by the way, but I'm going to try to somehow succinctly capture it all. But it turns out that if you go back, and this is done recently by Paul Rimmer, and look at all the different measurements and see like what people have explained and what has been left unexplained, it's quite an interesting story. So first of all, there is some, and by the way, I have this little code at the bottom if you want to decode what all these molecules are. First of all, there's been oxygen measured in small amounts to about part per million levels in the cloud layers. And this was done independently by both the Russian Venera probes and also by the NASA Pioneer Venus probe. That's kind of curious and nobody knows why it's there. There's actually a very tentative detection of ammonia gas, which really does need to be confirmed. Then there's also a tentative detection of methane and other hydrocarbons. Those are most likely contamination. But in this model, if you're looking and decoding these molecules, I'm also showing you some water vapor and some sulfur dioxide. And these are really known to be present, but their abundance profiles, how they change vertically in the atmosphere in the cloud layer, is actually not explained at all. And so my team built upon, okay, so let me see, I think I've got to back up for a second, but there's been a recent paper by Paul Rimmer. He's from Cambridge, UK. And he had this really interesting idea. He postulated that perhaps salts are getting uplifted from the surface, and these salts get absorbed by some of the cloud droplets. And in the process, they act as a buffer and partially neutralize the cloud droplets. They're still very acidic, but not as acidic. And then sulfur dioxide gets absorbed into these cloud droplets, and there's then a kind of deficit of sulfur dioxide in the atmosphere. So I'm now going to talk about only this plot on the left here, which comes out of a photochemistry model. This is about sulfur dioxide, so I'm going to walk you through this. On the left side, this is height above the surface in kilometers, and the x-axis is mixing ratio, which if you don't know what that means, it's a kind of weird jargon just for like a volume ratio of a gas. I'd like to draw your attention to this dotted purple line, which is sulfur dioxide in a base model of the atmosphere with photochemistry. So I want you to think about sulfur dioxide coming out of volcanoes on Venus and populating the atmosphere, mostly uniformly until a very high altitude where ultraviolet radiation would destroy sulfur dioxide. But that's not what we see, which are these gray points. The gray points with uncertainties, those are actual measurements, okay? So what you're seeing is not the sort of uniform sulfur dioxide, but in this cloud layer here, between about 48 and 60 and higher kilometers, there's actually a depletion of sulfur dioxide. If you read it off this x-axis, it is quite a lot, actually, a few orders of magnitude. Now take a look at this dashed line. And the dashed line is actually a model that assumes artificial fixes to match the data. And if you dig into the literature on Venus's photochemistry models by people, pretty much everyone has to do this, has to have some kind of artificial fix to fit both sulfur dioxide and water vapor. Now I'd like you to look at the solid line. It's not obviously a perfect fit, but this solid line has no artificial fix to the data. This solid line makes a bold and out there assumption that there's life in the atmosphere of Venus. And I want to walk you through this theory because it's a little specific. And then I'm going to give you some general discussion. So you can just sort of look at the bullet points on the left, the image on the right. The image on the left is just illustrating some of these molecules. So there's oxygen present at tens of parts per million. There's a possible presence of ammonia in the atmosphere. The vertical abundance profiles of sulfur dioxide and water vapor are not well explained. And there's an unknown lower cloud large particle composition. The hypothesis we're putting forward is there's life, some kind of microbial type life in the clouds producing ammonia. Now, we don't know for sure if ammonia is in the atmosphere, but it might actually be there. This ammonia gets absorbed into the cloud droplets, some of it, and neutralizes the droplets to less acidic than the droplets are without ammonia. The droplets trap dissolved sulfur dioxide. And curiously, the most energy efficient way for this hypothetical life to produce ammonia, the reaction also generates oxygen. So as a consequence of this idea, we actually resolve all of these listed atmosphere anomalies. And some of the droplets are predicted to be what we're just calling ammonium salt slurries. So what I like to say about this theory, and by the way, we have a paper under review. If you'd like a copy of the paper, I can send it to you as long as you don't share it around. Just send me an email. So I just want to say one thing at this point. I gave you a very quick high-level summary. I look at this situation as pick your poison. You can explain the data by artificial fixes to your model. You can imagine so much salts being uplifted from the surface, way too much that makes physical sense to neutralize the droplets. And then after a cascade, explain the profiles of sulfur dioxide and water vapor, but that doesn't help with ammonia and oxygen. Or you can pick the more out there concept of life in the clouds, which it has to be producing ammonia, and then it has a cascade effect to explain all of these things. Well, the great thing about Venus is we can go there. And indeed, NASA is planning to go to Venus with 2 different missions. ESA is planning as well. But to my knowledge, they're not looking for any of these things. None of them are probing the cloud particles directly with a probe in the atmosphere. So I've been leading a concept study to go to Venus and to revisit some of the issues that I mentioned, because a theory is just a theory, right? No matter how crazy or solid your hypothesis is, we need actual data. I'm really pleased to tell you that we are going to Venus on a mission with the Rocket Lab, Rocket Lab. Rocket Lab is planning a launch in 2023. Rocket Lab will launch a rocket with a cruise vehicle that will drop a very small probe into the atmosphere. Okay, this slide is out of date. Our payload is up to 1 kilogram in mass. The probe will go through the atmosphere and last about an hour, but it will take measurements while the probe is in the clouds. There's no parachute. So during the cloud, in the 20-kilometer vertically thick cloud layer, there's in the 20-kilometer thick, it's just going to last for 3 minutes. And we're going to, search for evidence of life in the clouds. What we're going to do is have a tiny instrument. We call it an autofluorescing nephelometer. That's a lot of words. But autofluorescence is a way to detect organics inside cloud droplets. On Earth, many organic compounds fluoresce when subject to an ultraviolet light. So we're going to have a little instrument with a laser. It'll shine this laser light out of a window in the probe. And if there is anything interesting, it will fluoresce. Of course, this doesn't mean there's life there. It could mean that there's this organic chemistry starting from simple organic molecules in concentrated sulfuric acid, but it would sure be interesting and motivate us to go back for something more detailed. This autofluorescing nephelometer will also measure the backscatter light into a certain angular range of both intensity and polarization. And from that, we'll be able to tell something about the shape of the particle. We'll be able to learn the shape of the particles and the index of refraction, which will help us understand the composition. We're very interested in these mode 3 particles of unknown composition to see if they might indicate even like a habitable environment for some kind of life. Okay, so this is a little picture, and you won't have time to read all of this, but it's a little picture and table of a commercially available instrument that goes on the outside of aircraft and does what I was telling you. It does mostly, it doesn't do the fluorescence, but it does the backscatter. And this is done by Droplet Measurement Technologies, who is building the instrument for our mission. So switching topics for a second, we also in our study came up with a medium mission where, reminiscent and inspired by the Russia Vega balloons that went to Venus in the late 1970s, we would send a balloon to Venus. And this balloon would last for about a week or so, maybe 2 weeks, and it would have very specific measurements. The one we're really most interested in is to actually understand the acidity, the pH of these droplets. Because if they're not as acidic as we thought, either by salt, particles being uplofted or life neutralizing its environment, we really want to know about that. We'd like to really detect the amount of water vapor, because right now the atmosphere is so incredibly dry. We'd like to know if there are pockets with higher humidity. We'd like to detect and identify metals in the cloud particles, because as we talked about before, metals are needed for at least life here to catalyze reactions. Okay, there's a lot more here. I want to wrap up so we have time for a bit of Q&A, but I want to tell you how excited I personally am for a series of astrobiology missions to Venus. If any of you have interest, please get in touch with me. We're confident we'll do the first mission, we will get to our medium mission. It's more pie in the sky that a large part of the community is interested in sample return. We know about Mars, people talk about other bodies, but we could go to Venus and do a sample return, not of the surface, but of the atmosphere, which is very challenging and hard. We can imagine bringing home some of the cloud particles so we can really see what's going on. So in conclusion, I would like to thank the sponsor of our study, Breakthrough Initiatives. And there's thanks here to a number of small space companies who helped out with a lot of the instrument and engineering thoughts. So our goal is to go to Venus to measure gases, to look at the droplets, and to see if there's any chance that Venus is habitable or any signs of life on Venus. Thank you for your attention.
Thanks a lot, Dr. Seeger. And we'll move into the Q&A. The first question is, Dear Sarah, if life does exist on Venus, how would life be restrained by the conditions of the atmosphere from developing into so-called complex forms?
Sorry, I was just reading a different question, so I didn't hear that. What is the, oh wait. Okay, so there's a lot of reason why, well, we're not experts, right? No, none of us know what's going on Venus. However, it's very nutrient limited. Like think about life here. We have tons of nutrients, right? We have stuff running off from the land into the ocean, lots of minerals, lots of metals. This atmosphere, as far as we know, is like starved for things. So that's probably the main reason life can't evolve into something more complicated. While you're thinking of the next question, I do want to ask this one about, it says from Simon, when I did A-level chemistry, the impression I got was that spectrometers proved beyond a doubt what a compound element was. Given the debate over phosphine on Venus, I presume that is not the case. A lot is open to interpretation. So there's a mass spectrometer and there's like a gas spectrometer. For the mass spectrometer that went into the atmosphere of Venus on Pioneer Venus, what that does is it actually ionizes the compounds and then subjects them to a magnetic field. And based on how they're deflected, it can tell something about the mass. And in that case, we see the parent ions. And so you have to piece together what's the most likely compound that the parent ions originated from. With respect to, I didn't give the whole talk on phosphine and how we detected it. With actually radio telescope, it's measuring an absorption feature. And if you are confident and believe that there is a signal there, you have to ask yourself, what other molecules can it be absorbed at the same wavelength range? Now, in this case of this radio telescope, we only saw one single line from phosphine. Usually you want to see many lines so you can robustly associate it, like you say, prove beyond a doubt what compound element it was. In this case, we only have one line, and there is some push that it's not phosphine, it's sulfur dioxide, which unfortunately has an overlapping feature. So in the clean lab, when you can get as much information as you want, maybe it's you can say something beyond a doubt. Okay, I'll turn it back over to my moderator.
Wonderful, thank you. Let's throw it to Altspace VR. Right now, they have someone who's ready to ask a question from the virtual reality space. So Altspace VR, take it away.
Thank you so much, Sarah. I wanted to ask you, I understand that we've seen no meteorites that we know of that have come from Venus, unlike Mars, where we've seen quite a few. That makes me wonder, would the sample return mission be significantly more difficult than what we just initiated with the Mars sample return missions? Would there be greater need for fuel or anything of that nature? Could you talk a little bit about that?
Sure, yeah, we probably wouldn't need a greater need for fuel, but we're not intending to go down to the surface of Venus because we're interested in the atmosphere, and down at the surface, there's like a much higher pressure and the gravity is much higher. Actually, the gravity of Venus is much higher, so we will need more fuel. The main challenge is we want to capture part of the atmosphere and launch like from a balloon. And that really hasn't been done before, although there's some small companies wanting to do something like that here on Earth. So, probably I don't know, in my mind personally, I mean, there's a lot of challenges, but I don't think it's more challenging than our Mars sample return. And indeed, we'll be borrowing heavily from that.
Excellent. Thank you so much.
All right, next question is from Stephen. And Stephen say, can you give us a mass balance estimate? How much ammonia is required to reduce the pH of concentrated sulfuric acid to between 1 and -1?
Okay, so unfortunately, I don't have that number in my head. I'd have to look up my paper, which I don't have time to look it up now. You need a lot of life, but not, I don't have that answer for you right now, but I could look it up and give you an answer if you email me the question.
Thank you. So a question from Jeff, how much will the 2023 probe mission cost and how will it be funded?
This so far is a privately funded mission. The bulk of the cost is funded out of Rocket Lab. They have I don't know how Rocket Lab is funding this. I'm just assuming that they have a private donor. We're right now, we're actually still raising money. So we have funding for the instrument and we have a couple other things we're still trying to get money for. But this is, so far, it's a purely privately funded mission.
Thank you. Next question is from Moxon. They say, what Venus atmospheric measurements are possible from Earth orbit? Can you look through the Venusian atmosphere while it's moving across the sun from our point of view?
Yes, actually, you can do that. That's called a Venus transit. The transit happens in pairs, unfortunately, only every 120 years. And the last time it did this wasn't that long ago, it was 2012. So if you're like one of those biohackers for longevity or can find a way to live a long time, you could do that in the future. Now, it's hard to observe the Venus atmosphere from here because the clouds are so incredibly reflective and they make a kind of barrier to really see what's beneath. We've tried to search for phosphine gas at infrared wavelengths instead of the radio wavelengths where our detection is, and we haven't had any success because we can only see above the clouds actually. So we can do stuff from Earth. People do measure sulfur dioxide, they measure water vapor, but we really want to send a probe into the atmosphere to make some gas measurements. And NASA, one of the missions, Da Vinci, is going to send a probe down and measure some gases.
Great. So we have 1 minute left, but maybe there is time for like one more very quick question. Let's see. If there's anything you see, please feel free to answer. But if not, then I'll ask a question from Amit. And they say, should an orbiter be used for up-close spectrometry?
Yes, but it has, and they will do that. The new missions going to Venus by NASA and ESA will definitely be doing that. The thing is, we're very interested in the cloud layer. It's incredibly vertically thick, 20 kilometers. And I forgot to mention this earlier, but the clouds completely cover the entire planet. Not like here on Earth, where sometimes it's cloudy, sometimes it's not. Some areas are always cloudy, some areas are rarely cloudy. And so even an orbiter cannot penetrate the clouds for some gases of interest.
Wonderful. Thank you very much for the presentations and for answering the questions. Again, if you do have time to answer some of the questions by text in the Q&A panel, that would be amazing. Thank you. So the next speaker is Barbara Belvisi, CEO of Interstellar Lab, and they will be talking about sustainable space settlement.
Hi, everyone. Hello. Hi, I'm very happy to be with you today. So my name is Barbara. I'm the founder and CEO of a company called Interstellar Lab. And I'm going to tell you a bit more about what we're doing and the system we're building for the Earth, the Moon, and in the future Mars. Okay. I think it's working now. Okay, so that's us. So we're a company, a American French company actually, and we've been out there since September 2018. We're a team of 20 people, and we just opened our first facility to start the mounting of our first system. So very exciting time and a lot of updates since last year for those who've been watching my presentation last year already. So what we're doing, our job is to design and to build a deployable system. So we're working on inflatable structure that can help the human live in a more sustainable way, whether it's on Earth and in the future in space. So more specifically, what we've been working on for the past years is to develop environmentally controlled module where you control inside all the atmospheric condition, the humidity, the temperature, the O2, the CO2 level, and you can grow food and at the same time have a regenerative approach, a sustainable approach, where we can recycle the air, the water, and the waste. The first system that we've been designing is for terrestrial application, and our goal is to test on Earth and to develop system for Earth before we can develop a system for space, and it's going to be step by step. First, low Earth orbit, then a lunar station, and then Mars, that we see more in the 20 coming years. A little bit more about how we design our station. So it's called eBIOS, which stands for Experimental Bioregenerative Station, and it's composed of several modules. Here you can see there is the tunnel module that is allowing us to connect one flower. This is what you can see right now on the screen to another one. You have 3 biopods. I will explain a little bit more what they are about. Those are the structure you can see on the right with the transparent layer. At the center, you have a connector on which you can connect different pods and the different module. You have an entrance door and you have the habitat section. And the habitat section, which is a combination of a 3D printed structure and a deployable inflatable structure inside. All the system has been designed to be completely modular, and they can work as standalone pods, but also plugged together. They form the station. So what was very important for us, and you can see here a fully plugged station. You can switch. You don't need to put a habitat section. You can decide to do only flowers with only greenhouses and aeroponic system. It's a very modular system, and we're trying to recreate here redundancy because each pod is working by itself. So each pod has its water system, its atmospheric system, its control system, and of course, when you plug all the pods together, you have a kind of a network effect where we're trying to compensate the different level of O2, CO2, water with the connector at the center. But otherwise, we're recreating and we're separating all the pods because of course, if one system goes down, you don't want the entire station to be impacted. So each pod is really separated from the other in the sense that it works by itself, but connected by sharing the resources they can generate. So that's an overview of the experimental bioregenerative station. So this one, we designed it for a group of 10 astronauts, and it's combining different, and it can support a group of 10 astronauts. And it brings the food, the water. We have a waste treatment unit, and also we recreated a greenhouse. So that's an aeroponics unit, which is purely dedicated to food production. So we've been working on a couple of design iteration on the aeroponics system. So aeroponics, it's when you spray droplets of water at the roots of the plants. So we choose the system because it's very it's consumed much less resources, much less water, and it goes directly into and the nutrient solution goes directly into the roots. And also most of the plants can grow actually in an aeroponic system, and it's allowing us to have different type of cultivation, whether it's purely vertical vertical, horizontal, or what we call A-frame with a little slope. And so this section, this dome, is completely dedicated to food production. And here, the strategy why we're also isolating one dome from the other is because here we want to boost the level of CO2 in opposition with the habitat section, where you don't want to boost the level of CO2, obviously. The second unit is called the greenhouse unit, and this one is really designed to fulfill the physiological needs of human beings, and also to grow some of the trees that can provide some fruits that we can't go in the aeroponic system. The treatment unit, so as I said before, each unit works independently. So it has its own water treatment purification system, its own atmospheric system, but still there are some waste that we will not recycle at the unit level, and there is a dedicated unit for the human waste and for the organic waste as well. And so that's the treatment unit here, where we plugging in different system for the waste, human and the black water that is not treated at the pod level. The habitat section I already told you about, which is a combination of a 3D printing structure and an inflatable dome in the middle, and the tunnel on the right side. Last year I presented for the first time what the code name was Baby Dome. Baby Dome was a smaller version of the aeroponics dome. And since actually we presented the Baby Dome at the Mars Society last year, we received a lot of demands, and we changed a little bit our approach and our business model, and we've been working on them on the manufacturing of the biopod. So we did a lot of iteration design to have a product that we can easily manufacture. So right now we are moving into a phase where we are finalizing the composite base. So as you can see in this picture, the biopod is composed of a white composite base, and at the entrance an airlock and an inflatable membrane. So it's a completely air supported structure, an inflatable membrane which is composed of two materials. And so this biopod we're going to manufacture 2022. So the first one will be assembled in Paris. The initial plan was to assemble in the Mojave Desert, but we had to change a little bit our plan. But I'm very hopeful we're gonna bring the second one in California by 2022, by mid-2022. And so the biopod it's a smaller version of the dome you've seen before. The aeroponics dome, the greenhouse dome, they're pretty similar. And it's this one in terms of size, it's 11 meter long, 4.5 meter high, and 6 meter wide. And this one, we use material for terrestrial application. So this one will never work on the moon and will never work on Mars. We will need to change the material system. Here we are using a PTFE and ETFE, and we have multi-layer with air chamber. What we're exploring for lunar and Martian application will be to have several layers, of course, of material, and including around 7 centimeters of air and 5 to 7 centimeters of water to try to recreate a shield that will protect from solar radiation. But we're not there yet. We have a whole plan of getting there. But the first idea with the biopod was really to get a greenhouse here on Earth where we can test our automation system. So that's another render of the biopod. It's gonna the first one is gonna look really like this. We're finalizing. We're working on the molding parts right now to assemble the composite base. So that's a view from the top. We like a biomimicry, so you can see here a lot of inspiration from some insects and some different code and reference we've been taking from nature. And so inside the biopod, we're combining aeroponics technology with greenhouse technology. If you don't want to have a greenhouse and you want to go full aeroponics, that's also something which is possible, because inside all the system is completely modular. That's another view from another angle. So at the entrance you have an airlock with a double door, and we constantly maintain an overpressure inside the dome, as it's an inflatable dome, which creates a pathogen-free environment. And that's going to be, I mean, what is interesting is that this approach that we first started for space application, we discover actually there are there are a lot of right now application on Earth, and that's a system that is very sustainable for Earth. And so our vision for space deployment is really the inflation system before 3D printing. Right now, we don't believe 3D printing technology is stable enough to only rely on this for the first habitat structure. In our mind, it will go first with deployable system, and then we integrated with the integration of 3D printing technology. So the biopod is completely deployable, modular, and using durable material. As I said, we have a composite base, and that is folded in that. Is cut actually in 5 pieces that you can fold and unfold. So that's for the deployability. And you have a membrane that we just blow air inside, and then we create a air-supported dome structure. The atmospheric system, the air system is fully controlled and fully autonomous, checking what's of course the level of a pressure and adjusting the pressure so we can maintain the structure up. Inside, so it's mostly inside the composite base where we put all the hardware system. So the water treatment system, the water treatment unit, the nutrient dosing system for the plants, all the atmospheric systems, so including AC, a CO2 scrubber, auto generator, and everything is automatized. And so that's the main part that we've been working on with our embed system team and software team, is really putting a lot of sensors. And so we have a model of simulation of what's going to happen inside the biopod. We have data from the sensors, and then we have the intelligence of the system, which is really inside the pod. And so it's fully autonomous. So when we design it, we will try to have system that doesn't need to be controlled by mission control, and that can be fully autonomous. And that's where we think there is a lot of innovation needed, and especially if you think about long-term space settlements. And so inside, we have advanced crop cultivation technology. So aeroponics, as I was saying before, you can also put a greenhouse, but a substrate-based greenhouse. But it's we're reworking, to be completely honest, we are reworking right now on the design of the greenhouse, because we might do a different version of the aeroponics system for small trees. The automation, so that's one part that we believe is super important, whether it's on Earth or in space. And before going to space and putting an automated system, we need to test one here. So that's what we do right now. So it's all about, of course, the control of temperature, the control of humidity, checking the water level in the tank, recapturing the water back in the environment of the dome, and checking the light intensity so we can turn on and off the LED depending on how much light the plant's been receiving. We have several software that we've been developing. I think last year also I was presenting for the first time the crop selector. The crop selector is the beta is online and live. You can try it. So crop selector is an algorithm where you enter the number of people you want to feed and how much of the nutritional needs you will cover. And our algorithm helps selecting plants and organizing the culture inside a biopod. So knowing how much space we have inside the biopod, it will define how many biopods you need to feed people, and then which crop, and it will do a calendar for more than a year. So we're planning in advance everything that you can grow inside. And so to make sure we meet the nutritional requirements every day on a daily basis, and those are very wide nutritional requirements here. We're not talking only about carbs or protein, but we're going very, very deep into potassium, sodium, and vitamin B3, B12, and all of those topics, and really organizing the schedule over time, which is not very easy to do. So we developed this what is called an organic algorithm that is helping us defining the schedule to feed all the astronauts. That's some of the. So we've been interestingly, we've been doing not only food production for this one, but also we've been testing a lot on different crops, more specifically on flowers. So this is one of the flowers that we've been growing in aeroponic system here at the lab in Paris. We've been testing vanilla, and it's been going very, very well. vanilla do actually pretty well on the aeroponics condition. So of course, we're not going to feed astronauts with vanilla. This was for other application, terrestrial application. But yeah, if we can grow vanilla on the moon or on Mars, that would be pretty cool and actually pretty useful to have some taste in in your desert. So that's some basis of we've been running some experiment on which structure and which I'm losing the name in English, but what we should use to keep the plant inside their little structure. Here you can see some of the algae roots of our system. Here much interesting roots as well. That's one of the prototype, very early prototype of the biopod. So we call it Quark. Quark is an environmentally controlled pod. Inside we control the light, the humidity, the temperature, the CO2 level. So we have a bunch of sensors. Here you can see the two versions of Quark. A different sensor, we're measuring everything and everything is fully automated. So we're using the quarks to taste different species, to do kind of to look at how they are reacting under several conditions, to find what are the best environmental conditions for them to grow, the level of CO2, the nutrition solution, and also we're testing the sensor and the automation of the system. So that was a very good way for us to approach also the supplier assessments and we eliminated some companies that were not satisfied with their CO2 sensors. That's another plant we've been growing, and of course it's a smaller, not a souvenir, but clin d'oeil, we say a small wink to the first flower that have been grown into space. We also actually working on having one of our quark, but designed in another way, in a more rectangular, square way, and to ship that into space, into low Earth orbit in the 12 coming months. Nothing has been announced yet, but hopefully next year I will be able to share more information with you guys at the next Mars Society conference. That's a picture of our 3D model of a station, and the station I was presenting you at the beginning. This 3D model, we will put it in the Museum of Space at Le Bourget, next to Paris, under the space settlement section. And as I was saying, it's a very modular approach that we had for designing this station, and the design of the habitat section is going to change actually a lot, like the biopod design change, but the habitat section is going to change pretty much. That's a view from the top, where you can see the different system. Here you can see the view on the aeroponic dome with the aeroponic and A-frame tower that we've been working on. The landscape is actually a Martian landscape, like a lunar landscape, but it's a Martian one. I have some connection problem apparently. Okay, and that's another simulation, another render that we did, imagining if we put our biopod and our station on the moon. The station on the moon, as I said, there are a lot of iteration we'll need to do compared to the version of the biopod that we have right now. The first one is going to be on their material system, where it's not going to be TFE and PTFE for sure, but it's going to be a multi-layer system, and as I said, with integrated air chamber and probably a water chamber as well. The transparent part for lunar application is it's not really relevant in terms of letting the light get in, because you don't get so much light on the moon, but it's more on the psychological side of having and offering a structure that is open to the sky and to outdoors for human living inside. So that's something we will really try to push, and to have this transparent layer. It's probably going to be smaller than what you can see on this picture right now, but this is something we don't want to let go. So we'll try to find a way. On the On the deployability, so that's actually a picture for a short movie that we did for the deployment of a station on Mars. Probably maybe next time I'll share with you the movie, the clip. And so as you can see, as I was telling you, you can connect different flowers all together. And so, and you don't need all the time to put a habitat section. I think here on this one, I can upload. Okay. I received some notification, but here on this one you can see, so we form two hexagons, but you can actually play much more, and you don't need an hexagon shape. You can keep on, putting different pods all together and grow the full structure. And so it's to recreate this redundancy, and at the same time to have like separated station that can work standalone, but also plug together. So we have a smart way of managing the resources, but also we separate the system. So if one gets down, it doesn't jeopardize the entire structure. So yeah, thank you. It's time for Q&A. We have 10 minutes for Q&A, and I'm happy to answer your questions now.
Wonderful. Thank you very much, Barbara, for the presentation. We have a lot of interest and a lot of questions. So let's see. All right, so we start with a question from Ahmed. They say, how is the ground cleared to allow for an even surface, so no roots or no sharp rocks under the pod?
Sorry, I missed the beginning of the question.
How would the ground be cleared in order to allow for an even surface, so like a smooth surface, so no roots or sharp rocks?
Inside the biopod?
Outside the biopod. So how would, I guess, how would you make sure that the pod doesn't, that, for example, like no plants grow under the pod, or there's no sharp rocks?
It's completely sealed. It's completely sealed. So there is the full structure is a completely sealed. So there is no communication with the outside world and the inside world. So the plants can't grow out there. Yeah, I hope I'm answering the question.
Great. Yeah, I also think probably the question could be like, how do you make sure, or do you place the pods on a very even and smooth and stable surface? Is this part of a consideration when you do place the pod, that the surface is very stable and smooth?
Yes, but so actually the pod is on small feet that we can adjust. So depending on how the terrain is, we can adjust the positioning of the pod. So we don't. So the purpose of the pod is actually not to have any foundation and not to do any work on the surface to be able to install it. So of course, if it's if it's very if the angle is not good, it's not going to be any way to install it. But otherwise, the purpose is really not to clean the surface before installing the pod.
Thank you. Next question comes from Thomas. They say, why isn't the structure fully inflatable? Wouldn't it be easier or cheaper to transport?
Yeah, it's a good question. So we're probably going to change a little bit the design for bigger domes. For this one, which is like 60 square meter on the ground, having a base, a composite base, it helps us, get something that is a pretty heavy and solid, that is structural actually to the entire dome. And inside we have all the hardware system, and all the hardware system is pretty heavy. And so we decided to have this shell as a structure, as a base structure, and then the inflated dome on top of it. Right now, and we also need the connection with the door. So that's why we design it. But right now, what we think, and especially for much bigger dome, is that the airlock, we'll keep the airlock with part of a composite structure, a beginning of a composite structure, a composite base where we're going to put all the hardware, but then all the pods going to be inflated. So we're going to reduce the rigid part of the pods. It's a good question.
Thank you. Next question is from Jody, and they say, what effects on plant growth do you think lower gravity on Mars will have? Any plans or ways to test this?
So of course the first step for us will be to to leverage on all the experiment that has already been done in the International Space Station with for instance, the VG system of NASA. We have a roadmap where we want to send several species into space and to see how they're reacting. We're pretty optimistic on the. I'm not a plant scientist. I'm not the. I'm not going to be very technical on this one. Some people in my team might better answer the question, but I'm pretty optimistic on the capabilities of plants to grow under low gravity environments, and we've seen that in the space station already. We've seen also that there are plants that develop interesting reaction into low gravity and create more molecule that can be very beneficial both for medical and pharmaceutical application. So we'll see how it goes. But this, for us in our roadmap before we go to Mars, the plan is to keep on launching a small structure into space and to see how plants are reacting and to test a lot of varieties of species. Then we will be able to answer, with more data and a more scientific approach this question.
Thanks. Next question from Dusty. They ask, where in the USA will you set up the biopods? Will it be a partnership with current analog programs, or will you do it on your own?
A partnership with who?
With current analog missions like Mars or B2 or MDRS?
Okay. Yes, it can be partnership with several structure. We're already talking to some of the people you just mentioned here. The first one, I still don't know where we're going to put it, whether it's California, Utah, Texas, Florida, we'll see. But it's going to be in collaboration. It's going to be, so we have customers, we have people who are buying the biopods that we're going to implement there. Yes, several options.
Great. Next question is about the application of the biopods here on Earth. So the question is, has the pods concept been considered for deployment in terrestrial applications as a response to the impact of climate change for agricultural production and for water management efficiencies?
Yes, yes, we're selling the pods at 200K on Earth, and we already have a 70 demand of pod, so which is a pretty good, even though we don't have our first pod full scale up and running, and the main application is a food production system, so sustainable food production system, because we're recycling a lot of the water, we use less energy, less resources that traditional indoor farming system. The second application on Earth is for the production of plants, so we're working with big brands like LVMH and some other famous fragrance and botanic ingredients companies that are interested in recreating specific climatic condition and to grow specific plants. So there are actually tons of terrestrial application. Other type of terrestrial application is for research and looking at how plants are reacting and playing with the different conditions. So it's really like a full. Think of biopod like a huge phytotron kind of, where you can grow whatever you want. But yes, it's right now the main application is for sustainable production of plants, for cosmetic and for food production.
Thank you. We have a lot more questions and 2 more minutes left. So let me ask one question that has been asked twice, and it is about the trees. So they say, both Nita and Jeffrey ask, what challenges do you anticipate in growing trees, such as walnuts? Is additional light provided?
Additional light, yes, I didn't mention that, but we have a different LED system, and of course we play with the spectrum depending on the type of plants that we're growing. Challenges with walnuts, I don't know yet because we haven't been growing walnuts in our system. Walnut tree, it might use a lot of water. But I think the main challenge with trees is actually how you maintain the structure So aeroponic system is great for small plants and tomatoes and a lot of different like roots vegetables. But with trees, there is this problem of having a structure that will hold it, because there is no soil, so you need to hold the tree. And this one we're gonna try different system, but it's a bit soon early for me to reply to this question.
Great. Well, thanks a lot, Barbara, for presentation and for answering the questions. And
course.
as always, we have a lot more interest here going in the Q&A panel. So if you have some time to answer, that would be amazing. Otherwise,
I
we
will.
are looking forward to seeing all of your ideas come to fruition and
Yes.
thrive both on Earth and on Mars. Thank you.
Thank you so much. Bye.
Wonderful. Bye. Thank you. So our next speaker is Jim Cantrell from Phantom Space, and they will be talking about achieving economic space launch. Jim, are you ready to present?
I'm here. Can you hear me?
Yep.
Okay, I'm going to share my screen here. Stand by while I do this. There we go. All right. So, yeah, thank you for having me here today, Bob Zubrin, old friend. Good to see you again. I like these discussions I hear on the Mars Society conferences like this. Sort of, it brings me back to the early days in this business. The far-reaching thinking and so on. I've been in this business 30 some odd years, and I guess I'm sort of at the more pragmatic end of it these days, trying to actually create things that are tangible and so on. There's room, for both sides of this in the whole discussion. I'm listening to the last one on growing plants, and thinking, this is the stuff we'll see in 30 years from now. It's really, really cool to see it on the front end of it. So what I'm going to talk about today is achieving low-cost space access. And this is something I've dedicated probably the last 10 plus years of my life to, and was involved in SpaceX in the early days. As you probably also know about Bob and his early involvement as well. So at any rate, it's been something I've been working on for quite some time here. The need for low-cost space access is not new. You may say, wow, this doesn't look like the shuttle. This is one of the very early designs of the shuttle. This started, roughly about the time we were sending astronauts to the moon. NASA started thinking about how can we go into space more economically, and recognizing there's always a budgetary limit there. And what they came up with was the shuttle. I would maintain that it was probably 20, 30 years too early. And with the technology we had in the 1970s, which is really what the shuttle was built on, this is what we came up with. And of course, the Soviets had copies, and I've been over and actually put my hands on those years ago, but they didn't look a whole lot different than ours, I can tell you. The shuttle ended up being very expensive. It had a cost that was, by the time things were really flying, it was about 5 times what the typical expendable vehicles would cost. You think about it, it makes total sense that you send 5 people up with a ComSat to place it in orbit. There's a lot of extra engineering, extra everything to go along with the people going up. So it's not really surprising that it ended up being so expensive. SLS, as it goes, by my calculations, is 10 to 15 times the typical expendable cost. So we're not learning anything there, at least at the NASA level, on reducing costs. So one of the things that you find when you start looking at vehicle costs, I know this is a chart and a lot of data and stuff, but basically the vertical axis is the cost per kilogram to send something to space, and the bottom is the launch capacity. And nobody buys their ride on the cost per kilogram, but it gives us an interesting way to evaluate the relative efficiency of the vehicles. And what you start to see is, there's a natural tendency for larger vehicles to simply be more efficient on a on a cost per kilogram basis. And so you've got a lot of the smaller vehicles that are coming along, Rocket Lab, Virgin Orbit, are fairly expensive in the cost per kilogram, but they're up there surprisingly with where the shuttle was. But then SpaceX, building the bigger and bigger vehicles, getting the cost down, and there's a number of factors in SpaceX getting their cost down. One of them is just simply the size, and so just keep in mind that one way to get the cost per kilogram down is to make a bigger vehicle. And if you want to launch a lot of small satellites, then you just pile them on sort of like a porcupine and throw them off into space. And that's really what's going on in the small sat arena is we're using the bigger vehicles with what we call ride share and put a lot of these smaller satellites on board. So SpaceX is really the low cost leader, and they're Falcon Heavy, and then now Starship are just getting bigger and bigger. So that's driving the cost per kilogram down. Excuse me. But the real question is really where does that go? What's the real cost to put, say a small satellite into orbit? And a lot of what I deal with in the commercial side, I've given up the government programs about 20 years ago. And in the commercial side of things, we've seen more and more small satellites becoming the thing to do, and that's a growing part of the market. So there's an interesting, I think, competition growing between the large expendable or even reusable vehicles. Let's just call it large reusable, and then the small mass manufactured vehicles. And really, they're two simply different classes of things. It's like taking the bus if you want to go somewhere versus driving your car. It's really a similar sort of comparison. So two economic systems in the launch that are developing. Reusability in all cases applies to both small and large, and it does reduce costs. There's a lot of non-recurring engineering in here, and if you go through the calculations, you find out that you only start to recoup your non-recurring engineering after about the 10th flight. So SpaceX is starting to do that. There was one booster they flew recently. I think it achieved 10 flights. But the main thing that it does for SpaceX, for example, is it gets the logistics down to a point where they can have fast return on these vehicles. And if you have a large number of people working for you, and you can double the launch by just going to reusability, just not even factoring in the cost of the vehicle that you're saving, that doubling of your flight rate is a big way to save the money. So I argue that's a larger factor than the reusability itself. But we're starting to see SpaceX managing to get the reusability to the point where it's actually saving money on the per unit replacement value. So small satellites, in fact, I submit, are driving the future. If you go big, the main reason to go big is truly just to haul humans or larger things to the moon, that sort of thing. But the majority of the satellites that are going up are small, small being a couple hundred kilograms and lower. And a lot of this is constellation. So if you look at the future projections of the market, you're seeing just a huge number of these satellites, and it's driven by commercial money primarily coming into the industry. So all you have to do is watch how much money is being invested in the business to really give you a feel for the outcome of what the number of satellites are going to be on the other side. These kind of studies here come from Euroconsult data, which is, they go around and count all the satellites and so forth. But the other thing is to just watch how much money is going into the industry from private investment. It's still hitting records and growing. So I don't see this as a particularly overgrown estimate. A lot of people take issue with it, but I think it's very real. And I've seen we grew to 1,200 satellites launched last year, something like that. That's an enormous number, and that was a very real number. So let's back up to mass manufacturing. So this is Henry Ford, and I'm sure you all heard of him. And what a lot of people don't know or don't think about with Henry Ford is he really changed society. If you go back 100 years or more, and you looked at the automotive industry, cars were a toy for the rich. They were something that cost, and then your dollars, you know, $6,000, $7,000, $8,000, which is enormous. You know, it's like buying a Ferrari or Lamborghini today. And there weren't a lot of people that knew how to drive them. And in fact, Mercedes forecasts the total demand ever in the world for cars was something like 3,000 a year because of the limit of the drivers. Henry Ford came along and said, well, I don't buy any of that. And if I make these on a production line, I think I can lower the cost so that my own people can afford it. And so not only, he was a son of a bitch, by the way, by all accounts, but not only did he change the way cars were manufactured and lowered the price, but he also changed the way people had an expectation of being treated in the workplace. And so he was very revolutionary in a lot of ways, and changed our terrestrial transportation system forever. And people, of course, copied him as he went along on the mass manufacturing assembly line. And this is an example of one of his assembly lines back in the day. Probably this is like 1915, 1917, I would guess. And you know, you just roll the cars along, put them together rather than have one person, one car. This was one person, one station. So one guy would put just the tanks in, one guy put just the steering wheel in, and so forth. So this model took the cost down to about $400 or $500 a piece for some of the initial cars that came out of Ford's factory. So we've also done the same thing in missiles. So this is the Atlas missile. If you go back to the Cold War, when there was talk of missile gaps with the Soviets, there was talk of you know, the Soviets are on our shores, they're in our backyards, they're everywhere. There was this sort of mania. And it's pretty amazing to see this assembly line sort of Atlas vehicles. These are vehicles that were being put together in parallel, but nonetheless a form of mass production in this. So that fueled, you know, the early nuclear race that we had with the Soviets. That, of course, you know, had a branch off to the space race. But you know, just to say that we've never mass manufactured launch vehicles is not true. I would argue that we haven't mass manufactured them efficiently. So, but you know, these were things that were supposed to protect us from certain death and kept the peace, actually. So they did what they had to do back then. But interesting historically. So if you look at mass-produced vehicles and you compare what they can do on cost per kilogram, you get this effect called the learning curve. We see this in aircraft. We see this in everything that's manufactured. You know, when you start your first unit, it's very expensive. Typically, companies won't sell at cost, right? They sell at expected cost down the road. So there's a, you know, your first sales tend to be at a loss. That's why, you know, cars, for example, the Edsel is an example of a bad car that didn't sell. You know, Ford put, you know, several $1 billion into that car and made very, very small sales. So they were losing a massive amount of money on every one of them. But had they managed to get up to, say, 1 million cars, they would have made money. So every car you guys drive, I assure you, the first unit cost to the factory, if they stopped right there, was about $100 million. And you know, by the time you get to mass manufacture, you know, you can buy these cars for $25, $50, $100,000. Same thing in rockets, and you can see some examples here. SpaceX costs, you know, for the Falcon 9 are in the $1,500 to $2,000 a kilogram. So some of these smaller vehicles, and these are the ones we're designing at Phantom, are capable of getting down and being competitive with that, with, you know, total production units of, say, 400 or 500, which, you know, over a few years is not hard to get to, but you have to have the discipline and not change it every time. Everybody that's a engineer knows how that works, that they like to do that. So rideshare also has hidden costs. So if you want to ride together on a SpaceX vehicle, you know, you've got hidden costs of, you have to actually engineer the satellite to the specifics of this and do a lot of extra testing. A lot of times you don't go to the right place, so you have to have propulsion. And then there's additional costs of launch delay because you don't get to choose your destination. So as it turns out, if you just compare it on a cost per kilogram, with say dedicated launch, there's some additional costs that the satellite operators have to bear. So that's why, if you wonder why there's all these small vehicles coming about and getting funded, this is why. So there's a really compelling economic argument here. The big question is who's going to be able to actually build these en masse and launch them en masse, and those are two very difficult things to do. And that's where that race is in the small vehicles. There's an inherent attraction to dedicated launch on small. You can go where you want, when you want, and there's an inherent lack of delay. Some of these. I've been involved in 11 startups in the last 15 years or so, and almost all of them, as we've gotten to the launch phase, have had to wait enormous amounts of time. It gets very expensive, when your burn rate's in the tens of millions of dollars a year. Waiting another year for a single satellite launch gets very expensive. So it's very compelling. There's a strong draw from the commercial community. Plus, constellation replenishment. If you think about it, really only the small vehicles can do that, and there's more and more satellites going up in constellations every day. The market's really kind of evolved to, from a small satellite perspective to the SpaceX rideshare, and SpaceX has crushed pretty much everybody in this business. The Indians are still there, but SpaceX is really dominating a lot of it. Then there's a group of small launchers, and they're of various sizes, and I think they suffer a little bit from entering the market very early, and they made some decisions on the size of the vehicle and performance, and so they've got some limitations there. We at Phantom think we've got the solution where we can eventually arrive at a daily launch kind of cadence and do it for fairly inexpensive. When I talk about our costs, we're doing a lot of supply chain where we buy our parts, like our engines and so on. So we know exactly what our costs are. And, the thing will have to happen with us is working the learning curve to get the cost down as we go along. So, if you start to then look at the frequency of launch and the vertical versus the cost per kilogram, you can kind of see what I was talking about the large reusable vehicles being on the lower left-hand side. They're the inexpensive ones, but they're rideshare, right? And your costs then, tend to bump up the cost per kilogram. But that's something most people don't think about when they consider these things. And a dedicated daily launch kind of system, if we achieve it, will be really, I think, very, very attractive. However, it's got its limitations. It's small. It can't launch large things to the outer solar systems like we saw Lucy. Certainly couldn't launch the pods to the moon we just saw, and so forth. So there's a place for both of these things, is the way I see the market coming. And there's a lot of these companies like Relativity and ABL and Firefly who are seeing the inherent costs of the small vehicle at lower production rates, and instead of trying to solve the production rate and flight rate problem, they're simply making bigger vehicles. So we see this with Rocket Lab, who's going to make a bigger vehicle to compete with the Falcon 9 and so forth. So a lot of that competition is actually going to grow into that side of the market, is where we see it. So we're building something we call the Daytona. It's our first vehicle. It's about 450 kilograms to orbit. We believe we can sell this for $4 million and still make a pretty good profit. Our engine comes from Ursa Major up in Colorado. Our engines are qualified, so we're a ways down the road. We've been around quietly for about 2 years and haven't said much to anybody. We've raised a little over $40 million. We'll be, if everything goes as planned, we'll be doing our stage level testing this coming year, and then our first flight the early part of next year. And here's just some pictures of some progress, some hardware. You can see the engines coming out of Ursa Major at a production rate. They're learning as well as everybody else, how to move things into production. We've got our second stage in preparation for stage level testing and so forth. And we've been going through a lot of the qual testing on the engines and so forth. So a lot of progress. We don't talk about it much, but hopefully we'll show up on the launch pad and surprise everybody. So that's the end of my presentation. I'm happy to take questions or field tomatoes thrown at me or whatever.
Wonderful. Thank you so much. So as usual, we do have a couple of questions, and I encourage everybody to throw them into the Q&A panel, which is right next to the raise hand button. But we'll start with the questions that we have. And the first one comes from Adil, and they have two questions. Well, the first one is, when will we get to the single digits per pound in terms of the price per pound or kilogram in your estimate? And the second question is, are you also tracking the developments related to non-rocket related technologies?
Yeah, so first question, when will we get to single digit? And I assume you mean like $1 to $10 a kilogram. So I know a lot of people are speculating that Starship will do that. I'm taking a wait and see attitude. I do think that Starship is going to massively lower the cost. It obviously will, if you believe my data points, about how the bigger you get, the lower the costs are. And by that, that they'll get down around $100, $150 a kilogram. Whether they can reduce it further through reusability will remain to be seen. I don't ever bet against Elon Musk. He's been the one thing in my life that's consistently surprised me at every turn. Every time I've bet against him, I've lost. So I'm not going to doubt that they'll get there. I think that's a ways away. And the other issue with Starship is it's so large. I think they're going to run into a flight rate problem. Just because we see it, what we're doing with these small vehicles, people worry about the seals and getting disturbed by the noise and things. It's a big issue. It's a bigger issue than you think. And the small vehicles, that's one of the reasons we think we can reach 100 is they have a very small footprint as far as the environmental disturbance. But we're starting to see that pushback at Boca Chica now. If he goes out to on a oil platform or something into the Gulf, then that might help. But there's still that intrinsic issue. So we'll see how disruptive that really is to launching satellites. It's definitely going to be disruptive to putting people into space and big stuff into space. So I think like everything else, there's different parts of the market, and I think these things do coexist in the future. Then the second question was other forms of non-rocket transportation. Yeah, propulsion has not really evolved much in 50, 60 years. Maybe a little more efficient here and there, but by and large, it's still, massively lighting liquid oxygen, some fuel, and then blowing it out the back. And it's really primitive if you think about it. And there's a lot of technologies that people have come up with over the years. Electric, for example, is one of them, but there's not enough thrust there to get off the planet. So the real thing I would be looking for the future would be how do we get something that is a high thrust that can yet have a better performance off the surface of the Earth. And I'm not seeing a whole lot that's like going to be revolutionary yet, but maybe people are working on it and I don't know about it. But that's something if I had another 100 years to live, I'd probably be pursuing that.
Thank you. Next question is from Brian. How does Phantom's plan differ or align with Astra's plans for daily launch of small vehicles?
Yeah, we're very similar to Astra in a lot of ways. In fact, their new vehicles sized exactly the same as ours. We've got some key people that we've hired from there that we'll announce this week. So there's a lot of similarity between the two companies. But the reality is who's going to be able to create a daily launch. And as I look down the future, I think they'll be one of the ones that we actually compete with. I don't worry about relativity, for example. I know Tim Ellis, the CEO, personally, and I think their 3D printing technology is great, but probably wasted on rockets. And the rest of the guys are kind of chasing the Falcon 9, but I don't see Astra doing that. I think they're one of the true believers that in what I just talked about, which is daily launch. So I think we're going to be different only in how we implement it and how we manage it and go forward. So in any case, I think there's room for 2 or 3 of those kind of companies in the market, and so I don't worry about it. I just try to get up every day and do the best I can.
Thank you. Next question. We have seen a number of aircraft launched to orbit systems, and these seem to provide a niche in the available orbital launch options. So whatever happened to the raccoon concept? Is it just not engineering or economically practical?
Yeah, so if you've ever actually launched big stuff, big, even small rockets like we're talking about are big, and it's liquid, you have a real recognition of the practical difficulties you run into. And to put that on an airplane, more power to you. That's not something I particularly care to do. I've actually been involved with balloons, and same thing there. So I think some sort of air launch sort of thing can get you a marginal advantage that I think is eaten up completely by the disadvantage of having to put those systems remotely on a vehicle. They can be done clearly. We saw Pegasus for years. In fact, I flew a satellite off of Pegasus in the 90s. That was a solid rocket, and Virgin is a liquid rocket. And I understand from the people that work at Virgin, I have a number of them that work for me now. They would say every Monday morning started with, why are we putting the liquid rocket on the airplane? Shouldn't we put it on the ground? And by Tuesday morning, Richard Branson would come back and say, thou shalt put the rocket on the airplane, on the 747 with the Virgin logo. So there's a lot of reasons why you do these things, but I've never been a big fan of those. They're just technically complicated, and it's hard enough to do what we're trying to do without involving that extra step, in my view.
Thank you. Thank you so much for answering the questions and for the presentation. Oh, we actually have another one. It's from Dusty, and they say, do you know about JP Aerospace trying airship to space?
No, I'm not aware of that one.
Well, Dusty, if you could please maybe put the information in the comments or in the chat or in Q&A, that would be great. And again, Jim, thank you so much for the presentation and for the questions.
My pleasure.
All right. Well, next up, we have Dr. Sethivian Yu, co-founder and chief scientist of Helicity Space. They will be talking about fusion-powered Helicity Drive. Dr. Yu, are you with us? Are you ready to present?
Hello, good morning. Good morning, everyone. Thank you very much for having me. Let's see, I should share my screen, I think. So thank you very much to all the organizers, to Dr. Zubrin, for inviting me to represent a large team, reasonably large team involving academia, us, the private company, and national labs, to be able to talk about this new fusion propulsion concept. I'd like to acknowledge the support of the Limitless Space Institute and the Department of Energy for some of the work behind this concept. And also acknowledge the private investors behind the company who are among the first to believe in the idea. So the outline of the talk really is trying to answer three basic questions, really. Can we have fast and fuel efficient space propulsion? Address the elephant in the room, will fusion work? And then question three is really go into the details as to what is this new fusion propulsion concept and why it's different from the others. So, how fast do we want to go? Between Earth and Mars, the distances are typically in the hundreds of millions of kilometers, depending on their relative positions in the orbit around the sun. You have to go up this gravitational hill, and trying to get there as fast as possible. So you need a lot of energy to get there. And if you want to fly fast, you need a lot of power. And the typical velocities, and these numbers are really order of magnitude, is really just to give an idea. You need hundreds of thousands of kilometers per hour, kilometers per second delta Vs. The kind of objects that we've launched into space and the fastest objects, are listed on the left roughly to give you an order of magnitude idea as to how fast objects can go in space. They're very fast by our day-to-day purposes. And some of those velocities can approach, fast bars, interplanetary transportation. the question next is really how fuel efficient can it be? Now, I'd like to focus on the big payloads, things like human class type payloads, and typically, for example, you would launch people with all the support structure around it to provide life, and it'd be tens of tons per person that you need to be able to send at these really, really high velocities. So with existing propellant and existing rockets, you would need a lot of propellant mass, chemical propellant mass, to be able to launch and then accelerate these payloads to extremely high velocities. And although it's a lot of mass, of propellant mass, you can only burn it all for a few minutes, and then after that you have to coast. To be able to go faster, you need to carry even more propellant, so you get that rocket equation hurdle where you just get an exponential growth of propellant mass that's required and becomes quickly unfeasible. Now, to reach high speeds, of course, we all know that we need a lot of thrust power per unit mass, so the specific thrust. And these engines, the SpaceX Raptor, the Saturn V F1 rockets, have very high power. If you add it to all the systems, the starships, the space shuttle, and so on, it's still reasonably high enough power that you can go reasonably fast. Now, all these engines use chemical energy. So you would take this propellant, burn it out, and use chemical energy to exhaust the propellant out the back to push your rocket forward. If you want fuel efficiency, though, you want a very high velocity, exhaust velocity of this propellant. So the higher, the better. The maximum exhaust velocity is effectively limited by the amount of chemical energy you can carry. In this case, you can express it as a maximum temperature, which is of the order of 1,000 K and so on. So how do you go faster? How would you exhaust this faster to be more fuel efficient? Well, one option is to add a uranium core, solid core, to be able to increase the propellant temperature to a few thousand degrees, in a factor of 3 or so, a factor of 2 or 3. So nuclear thermal propulsion works, and one has flown and others are in the planning stages and would increase the fuel efficiency, which means that for the same amount of propellant you could go faster, or you would go to the same speeds with less propellant. So that's pretty good. Another option is to take electricity, put some kind of electrical power source on board, and then you accelerate the plasma propellant. And the idea is basically you use electricity and magnetic fields, electrostatic fields and electromagnetic fields to accelerate a cold plasma as fast as possible. And the advantage is you can really, really have high exhaust velocity. So, for example, the ion thrusters, would have a much larger exhaust velocity. And if you add it to solar panels and then you send it to Mercury, you have the Bepi-Colombo mission. You can also plan to do this with small nuclear fission power plants, similar to nuclear submarines, like the GMO mission plan with 200 kilowatt electric nuclear reactor to the Jupiter icy moons. Vladimir, you could put a 200 or 100 kilowatt electric. The hurdle is that these nuclear reactors are very, very heavy. The thrust, or the electrical power per unit mass, is not super attractive. You have to add radiators and so on. So the actual specific thrust is still reasonably low. However, it's very fuel efficient. So another option is just to take the electricity on board, and instead of accelerating the plasma, you want to heat the plasma. You heat the plasma now to 100 million degrees. At that kind of temperature, anything above 10 million degrees, you start to get fusion reactions. That releases 10 million times more energy than chemical energy, so you can do something interesting with that and really accelerate the plasma out the back at very, very high velocities. So, there's been lots of studies on magnetic fusion, on fusion, different fusion concepts, and I've given 2 examples here. One based on the spherical tokamak, where you would have 8 gigawatts of thrust, and then Spheromax, with about 3 gigawatts of thrust. And they start to become very attractive because they have very large specific thrust at very large specific impulse. You can really start going fast. Our concept kind of fits within the same kind of scales in terms of thrust and specific impulse. One of the major advantages, and we'll go into that is that we can actually dial down the power levels to something that is a little bit more near term, somewhat comparable to electric propulsion. And then if we deliver that, then scale up eventually up to the large, fully self-sustained, fantastic drives that we all want. So to put some numbers on this is the final plot with the numbers where you can see the main important part of the numbers is to go really fast to go to Mars in a month or so with a very large human class payloads, you want thrust powers of order of kilowatt thrust per kilogram. Anything above that is really nice. But then if you want reasonable fuel mass ratios, you want very high specific impulse. So the ideal interplanetary colonization, reusable rapid transportation system would sit on the top right here. Another interesting line that you could look at is the thrust to weight ratio. Many people ask, can fusion be used for launch? Well, not really, because you want a thrust to weight ratio that is larger than 1. So chemical propulsion is still the best way to launch a system. However, in space, these concepts would be a great solution. The numbers over here are basically to show the scalability of our concept, to go from something that is of the order of close to what exists in the near term to something that's scalable all the way up to the fully self-sustained power plants flying in space. So we need fusion. The question, of course, that everyone always asks is, will fusion work? So I have to give a quick overview as to how fusion works. The conventional way of doing it is to hold the plasma in a steady state with magnetic fields at a given density. And typically, you're limited by the strength of the magnetic field, so you're typically at the low densities. And then because it's steady state, you want to have steady state heating and slowly raise the temperature or rapidly raise the temperature to those 100 million degrees. So you're competing with the heat loss, the energy confinement time, the thermal insulation to be able to raise the temperature. It's a bit like boiling coffee. You want to put some heat in, but you have to compete with the heat loss. So a better thermal insulation means you have an easier time of raising the temperature. Now with magnetic confinement fusion, because you're limited at low densities, the only way to really increase the confinement time is to increase the size of the machine. So all these data points are all the experiments around the world over the last 70 years, or most of them anyway, and slowly and diligently moving up towards the black line, which is the Lawson criterion, which tells you when you're getting more energy out than what you put in terms of heating. So the progress has been slow but steady, and we're getting very, very close to the not the finish line, but the beginning of the finish line. And then these two experiments, ITER Sulfur Plant Spark over in Boston, is going to try and cross that line. The second conventional way of doing this is to use lasers and to ignore trying to increase the confinement time. What you do is you just hold a solid pellets and at solid densities, hold a solid pellet of fuel, and then use some radiations or lasers converted to X-rays in a very, very short pulse, short enough to be able to compress the fuel pellet to fusion temperatures before it disassembles itself. So you use its own inertia in doing that. So that works. There's been some fantastic results from the National Ignition Facility over in Livermore in California, where depending on how you quantify it, but you've basically effectively shown that you can cross this Lawson criterion threshold and get more energy out than what you put in. So, the scientific proof of principle of fusion, getting more energy out than put in, is feasible. Now, because you rely on the inertia, the only way to really go further is to increase the power and therefore the size of lasers to be able to compress these tiny little millimeter-sized pellets with lasers the size of football fields. And you need to go on increasing to be able to increase the fusion gain. So there's a third way, an intermediate way, which is like a Goldilocks alternative, if you want, variously called magneto-inertial fusion, magnetized target fusion, magnetized liner inertial fusion. And those are more recent concepts, and sometimes revisiting old concepts that were discarded but were rendered feasible with new discoveries and new technologies. So one of them is basically to increase, add magnetic fields. So these don't have magnetic fields, but add magnetic fields to improve the thermal insulation, and then continue compressing. Or use the magnetic confinement, but even though the energy confinement time is not very good, instead of increasing the size of the machine, you just compress it instead. And then the idea is, compared to magnetic confinement fusion, you have a smaller power plant normally, and compared to the inertial confinement fusion, you have reduced drivers. So this Goldilocks zone is eminently suitable, in our opinion, to space propulsion and power. So our concept, our first data point, if you want, from a precursor experiment, is around there. And the idea is, over our development path, is to move towards that line. Now, you can also plot the cost, overall cost of the expected cost of the system as a function of this density. So at low densities, you can see that magnetic confinement fusion is quite expensive. And then at the high density range, the compression drivers drive the cost of the fusion concept. While at the intermediate level, because of reduced size and reduced driver power, there's a minimum in the cost curve, which gives an optimum range. We are about there in terms of density. The heuristic way of understanding this is that the rise of the cost to the left is due to the size of the machine and the size of the magnets, and to the right, it's the cost of the lasers and the size of the lasers to be able to increase the density. And this one's to increase the confinement. So in terms of fusion propulsion concepts, there's been many. And this plot here shows effectively that thrust power, which is that number above 1 where we want to be able to go really fast around the solar system, again as a function of its density. So on the left, you have the steady state magnetic fusion, and then on the right, you would have the pulsed laser fusion, and then in the middle, you would start to have the magnetized particle fusion or the magneto-inertial fusion at the intermediate densities. And the diameters of the circles represent roughly the total mass of the fusion concept. Just to give you a relative idea as to how big and heavy these systems are expected to be. So you can see that on the left, the magnetic fusion one, like the spherical tokamak fusion mission to Jupiter, has hundreds of tons of mass. The inertial confinement fusion, like the Daedalus project, which is mainly for an interstellar mission, is very massive. It's thousands of tons, and not tens of thousands of tons. And the intermediate ones have potentially smaller and lower masses, which would be quite attractive. The other number that is interesting to look at is that these pulse concepts rely on a certain repetition rate to be able to have the power required for pushing large payloads around the solar system. The assumption for many of these pulse concepts are quite high repetition rates, hundreds of hertz or 30 hertz, tens of hertz at least, to be able to compress these plasmas either with lasers or some kind of liner. Our concepts in general are try to approach it with a more modest repetition rate, so 1 hertz is a reasonable balance between feasibility and at the lowest level actually much lower pulse rates, which is actually limited by the auxiliary onboard power supply. But in general, the idea is the masses are significantly smaller than the other concepts. So what is our concept? If there's only one slide that you want to remember, it's probably this one. This one is what summarizes everything. It's a pulse magneto-inertial fusion system designed for space propulsion and then at a larger scale for power. And exploits 3 key ideas. So these are based on experimental observations in laboratory. We've made all these discoveries in the laboratory recently, and we're putting it all together. So something called magnetic plectron to be able to confine the plasma. Magnetic reconnection heating to preheat the plasma after formation. And then we use peristaltic compression to be able to raise the energy density. Combining all 3 together results in quite a new scalable performance that doesn't exist, that has not existed before. The fusion triple products, so the performance in terms of how long you can hold the plasma and raise the temperature to fusion condition, has a new factor inside it, which is proportional to the number of plasma sources raised to some power. And that means that the number of plasma guns and the number of plasma sources, there is a new control node for us as operators, in addition to all the other fusion concepts that you would use, for example, the plasma current, the magnetic field strength, the plasma size, or the compression ratio. It means that with this new factor, we can compensate somewhat for uncertainties in the confinement time. If the confinement time is a bit lower, we can just increase, the number of guns instead. The other advantage is that to increase the power levels, you can spread the input energy required to generate fusion over a larger number of guns, which reduces the engineering requirements of each gun. The other thing is the development path can be quite rapid, because it's like cylinders in a car engine. You can test the idea very, very early on at modest cost, and then ramp up very quickly, because you just have to add more cylinders if you want to the engine, rather than increasing the size of a single cylinder. So the physics basis, what are these magnetic plectronines? The Mochi experiment that we built before as a precursor experiment has observed these very, very long-lived, stable plasma jets in the laboratory generated from one of these plasma guns. It's about 1 meter long, and it lasts tens to 100 microseconds, which is extremely stable. It's 100 times the instability timescale. And one thing that was exciting was that the magnetic field inside these jets was double helical, what we call plectronemic. It's like a double helix DNA strand that, if you want to have an intuitive picture, is a bit like a rubber band torus that is stretched, twisted, and stuffed into a cylinder, which is the plasma jet in this case. Our colleague at the Swarthmore College has an experiment where they discovered this first inside, not a jet close to in vacuum, but in a jet inside a closed cylinder with close fitting walls. And they discovered the same structure. So these plectronines have very interesting properties. They have helical shear flows, they're stable, and they can be manipulated and have a very long aspect ratio. And they're more stable than torus. The second physics basis is reconnection heating. If we merge multiple magnetic objects, the magnetic field lines can merge together and reconnect. And then some of the dissipated magnetic energy heats up the plasma. This was demonstrated around the world over decades using toruses, various types of toruses, and then recently with these plectronine double helical fields merged together in the center. And this plot shows basically the strength of the magnetic field and then the temperature that you would get out of it. And you can start getting fusion temperatures, which is above 1,000 here, reasonably with modest magnetic field, at least at low densities. And what we aim to do is to try and do this at high density. The third operation that we have is the magnetic compression. This is was invented by our colleague at Caltech, who basically set a series of coils in a transmission line setup that is tapered, and then you send a double current pulse through it, and effectively you have a traveling magnetic field that will start to increase in field and slow down. So the front of the field slows down and the rear of the field comes in and piles up. So if you trap the plasma in the center here, it will start in the frame of the plasma. It looks like an implosion and a compression. So the advantage of combining all that is that the compression ratio needed to reach fusion conditions, because of the preheating, doesn't need to be as high as if you did it purely by compression alone. So these are the steps of how it works. You form any number of plectronemic jets at the beginning into that front magnetic field. As it travels, the reconnection preheats the plasma and especially ions, which is compared to other standard heating methods or made steady state, neutral beams, charged particles, and so on. Radio frequency is internal, it's very high power efficient, and directly heats the ions and not the electrons. So then you can start raising this non-isothermal plasma to the thermonuclear regime over slightly longer timescales than the electron confinement time. And as it travels down the nozzle to the throat, it reaches peak condition. And then as the fusion reactions heat the plasma further, you can mix it with cooler propellant to augment the thrust and adjust the ISP. We've done preliminary numerical simulations. These are very preliminary pictures with Los Alamos to help us inform the design and the timing of our subsystem. And the key idea really is, and that's different from prior fusion concepts, is that the fusion output scales with the number of plasma guns. So you can see the plasma sources there. That means we have three different classes of engine, what we call small, medium, and large. And the small one is really the simplest possible idea. You just take some kind of power source, you create the fusion conditions, and then you eject it out the back with some kind of small gain. It doesn't have to be huge gain because you don't need to make electricity. So if you take a 100 kilowatt electric, you would get 50 kilowatt thrust, for example. That's at this level with X number of guns. That's what we call an fusion afterburner. The performance might not be spectacular, but at least it would be a fusion propulsion system in space. If you increase the number of guns such that the fusion power increases, you can add some power conversion system that adds extra mass, but this will contribute to the input power, and therefore you can start raising, for a given 100 kilowatt electric, start raising the thrust output until you get more thrust out than what you put in, effectively thanks to the recirculation of energy. And then of course, if the recirculation is such that it covers all the required input energy, that's a fully self-sustained fusion drive. And yeah, the sky is a limit. There's an upper limit in terms of confinement time. But this scalability idea means that you can start early and there's no need to wait for the full fusion drive. So these slides are a little bit detailed, but really it's a bit like doing a shopping list when you buy an engine, buy a car. On the left are the specifications, a detailed technical specification. On the right is roughly what the missions could do potentially. And the idea at the smallest scale is that we get not very high specific thrust, but it's reasonably low weight. It can be launched in a Falcon 9 rocket. If we have a 100 kilowatt electric power source, we will get tens of kilowatt thrust. And the idea is this development path is what we're focusing on, is to really start demonstrating this and then do the minimum viable prototype in space as soon as possible. These are some of the mission level figures in there. Now, if you go up much larger into like 20 guns, 29 guns, and so on, you can start getting quite a lot of thrust and power. And then we're thinking of studying missions, for example, in Cislunar as a heavy freight cycler, just to be able to show how fuel efficiency, even though it won't be fast to be able to take a cargo between the Earth and the Moon, but if you can do it over multiple cycles, you could reduce the cost from reusability in principle. And then, of course, what we're most interested in eventually in the long run would be the large and extra large scales, where it's fully self-sustained. You don't even need any auxiliary power, and you get megawatts of thrust and gigawatts of thrust at these large specific powers that open up the solar system to interplanetary transport, for example, a reusable cycle between Earth and Mars. For example, for 150 tons to Mars rendezvous, you could do it in a few months with the L scale and the extra large scale, which is a peak one. You could go really, really quickly. We're working on studies on future missions, like planetary difference, interstellar object rendezvous, and so on. So the stage of the company right now, we're at the early days. We're building on our new experiment to prove all this, to demonstrate all this. Hardware has been cut. You've seen the magnetic nozzle. That's already been cut. So a lot of this is going to be built very soon, built on past experience. So, I hope that this presentation provided some beginnings of the answers to the three questions that fusion propulsion could be a solution for fast and fuel efficient space propulsion. The question, will fusion work? As scientists, the proof of principle has been demonstrated. It becomes there's still some science to do, but there's a lot of engineering issues that everyone has to work through. And then what is the holistic drive fusion concept? Which is one of the new compact fusion concepts that's uniquely designed to be scalable and primarily for propulsion first before being a power system. So with that, thank you very much. And I'd be happy to entertain any questions.
Wonderful. Thank you so much, Dr. Yu. We have a lot of questions, and the first question is from Nicholas, and they say, how would the plasma source be replenished while the rocket was flying in space?
The plasma source are basically the fuel tanks. It's basically hydrogen, well, deuterium in this case. In our situation, we use deuterium fuel tanks. So, you know, the imagination is that we're going to have large liquid deuterium tanks, and then they will just be injected into the plasma gun.
Thank you. Next question. Is the exhaust toxic?
So the exhaust is mainly helium, because the fusion reaction from deuterium generates mostly charged particles in the form of helium. There'll be electrons, they'll be neutral. So that is not toxic. However, there are, if you mean by toxic, there's going to be neutrons as well that will come out. And the neutrons are extremely energetic, and neutrons impacting materials or impacting the human body can have detrimental effects. So there will have to be shielding, of course, to mitigate the neutron damage on materials and systems and payloads and so on. The fact that this is placed really far away from the payload, so this would be, for example, a human crew to Mars, is one of the reasons you want to be able to put the radioactive system, mildly radioactive system, as far away as possible. And then you would shadow this with a shielding system.
Thanks for the answer. Next question is from Thomas. They say, Dr. Yu, which materials would be appropriate for such high fusion temperatures at the nozzle?
Oh, so the nozzle, at these kind of temperatures, you use magnetic fields to thermally insulate these high temperatures from anything that's material. You really don't want to touch the walls with this hot plasma, because it would just melt everything. And it will also cool the plasma, which we don't want. So, the main materials would be, at the moment, there's many ways of doing it, but we want boron carbide shielding, for example, tungsten coated boron carbide as well. And then there'll be blankets to be able to thermalize, which was probably, we're thinking about it, but probably the best option would be liquid water, actually, as a neutron thermalizer and moderator.
Great, thank you. Next question comes from Douglas, and they say, couldn't one use neutron-neutron fusion to get around the Coulomb barrier?
Neutron fusion doesn't work.
All right, well, the next question is from Amit.
You need neutron star levels of densities.
Got it. So next question is from Amit. They say, are you revisiting the idea of heating plasma exhaust using X-ray laser while it is being ejected?
We don't use lasers or X-rays to heat the plasma. We're heating the plasma with magnetic fields. We believe it's much more efficient to do it that way than using lasers.
Next question, are you considering Z-pinching the exhaust to reach fusion?
This is very close to a Z-pinch concept. It has an internal current that is very, very close to a Z-pinch. You can think of it as a screw pinch. So a Z-pinch only has an axial current, and ours has an axial as well as an azimuthal current. So that's why you have this double helix system. But a lot of the physics is very, very similar. It's self-pinched, it's self-stable, thanks to shear flows. But instead of just an axial shear flow, we have helical shear flows that stabilize the plasma well. So the external magnetic compression is to come in addition to the self-pinching.
Thank you. We have 2 more minutes for questions. So I'll read one of the recent ones. How quickly and easily can this system be turned off in case of an emergency?
Since it's a pulse system, it's very easy to turn it off. In fact, most fusion systems, it's very easy to turn things off. It's very hard to start it. I think that's why fusion is taking so long to get there. If anything goes wrong, the whole thing just stops.
All right. And the last question is from Dennis. Would it be possible to accelerate the plasma at the output with the magnetic field, like a railgun, instead of compressing it?
Well, the acceleration with a railgun is not as efficient as converting the hot plasma exhaust as it expands out in a diverging magnetic field, like a standard nozzle effect. So because the pressure from the high temperature plasma expanding out to the magnetic field coils of that diverging nozzle generates a large thrust. Accelerating with a railgun, you would need very, very long distances, and then the acceleration force will decrease with the length. So railguns are not extremely efficient.
Wonderful. Thank you so much, Dr. Yu, for the presentation and for answering the questions. We do have a couple more in the Q&A panel. If you have a couple of minutes to just stay around and answer them via text. But if not, thank you again for your time. And we welcome our next speaker, Evan. So the next speaker is Evan Plante-Weir, co-founder of Mars Society Canada and senior blog writer at the Mars Society. And Evan, if you're ready, please take it away.
Hi, everybody. Okay, let me get my presentation ready here. Can you see my presentation?
Yes.
Okay, wonderful. So as mentioned, my name is Evan Plante-Weir, and I'm a senior writer at the Mars Society and co-founder of the Mars Society of Canada. I'm very grateful to be here, so thank you to everybody for this wonderful opportunity. I have no ingenious technical solutions for Mars settlement or groundbreaking research to share with you. Unlike the brilliant individuals I'm honored to be speaking alongside today, I'm not an engineer or a scientist. For the purposes of this talk, I'm simply a storyteller. And as we are all gathered together at this wonderful convention to discuss and ponder the exploration and settlement of the Red Planet, my talk today will be about how our journey to Mars will play an important part in defining our story as a species, the story of humanity. So what is the story of humanity? And where does Mars fit in? Well, of course, the nuance and complexity of that question goes far beyond a 25-minute presentation. No doubt, it will probably take us thousands of years to attempt an answer. But I believe that we can speculate with relative certainty as to how settlement of the Red Planet will impact a central pillar of that vast narrative. To begin, I'd like to pose a question. What is our relationship with life on this world? How do we conceptualize the relationship between humanity and our fellow Earthlings? Now, you may be thinking, this is not a simple question. And of course, you would be right. There are so many perspectives and variables to take into account, it's mind-boggling. And further, this question is complicated by the unpopular yet distinct possibility that life might only exist here on Earth. The only place where we know life to exist is here. And even if potentially habitable planets are common, we still just don't know how likely it is for life to take root on any one of them. Some theories suggest that the genesis of life is fantastically rare, and that it could require the confluence of so many unlikely circumstances that it has occurred only once, or is so thinly spread throughout the universe that the vast distances in time and space between islands of life make them, in effect, completely isolated. Now, that might defy our hopes and intuitions. Given the size and age of the universe, and given that life seems to crop up everywhere it possibly can on Earth, it certainly feels like life should be plentiful beyond the atmosphere. Personally, I hope that's the case, but we simply don't know. Given this possibility, let's return back to that tricky question, but ask it a little differently. What is our relationship with life? Broadly speaking, what is the story of our relationship as humans with the natural living world? Are we a part of it? Or does our technology make us distinct from it? Are we allies with it or adversaries? Are we caretakers of life or tyrants? There are, of course, many ways to answer this, but for the purpose of this talk, I'd like to single out one particular narrative which I believe will change in meaningful ways as we reach for Mars and become a multiplanetary species. Consider the following narrative. Humanity, the contagion. Humanity, polluters and destroyers of ecosystems. Earth would be better off without us. Have you heard that version of our story? It isn't hard to find. To one degree or another, this sentiment has become unfortunately common. What's more, it's understandable and at first glance, maybe even justified. For the past few hundred years since the Industrial Revolution, and perhaps as far back as 2,000 years ago, humans have inflicted large-scale damage on our planet. We pollute our air with vehicle exhaust and factory emissions. We pollute our water with industrial and agricultural runoff. We pollute and poison our land with garbage, fertilizer, and pesticides. And in this age of free-flowing information, this harsh reality is ever present in our minds. This is the source of a great deal of guilt and frustration, and sadly, it has become a prominent thread in the tale of our species thus far. So, is this the final word on humanity? Are we to be the antagonists of our own story? Would life on Earth, and perhaps elsewhere, really be better without us? Of course not. Though we don't hear about it nearly as often, humans also do wonderful things for the sake of our fellow Earthlings. We are gradually learning from our mistakes, and most importantly, our recent treatment of this planet constitutes only a small part of our story. That story began about 300,000 years ago in East Africa with the arrival of the first Homo sapiens. They struggled through millennia of immense hardship to carry our story forward to the present moment so that you and I, alive here today, can play our small part in sustaining it far beyond the next 300,000 years. Most of our story so far came long before we began to pollute this planet, and most of it is yet to be written. The ecological irresponsibility that, for some, has come to define our story since the Industrial Revolution is just one chapter of a far greater journey. And the next chapter will introduce quite a different narrative. As we establish a permanent presence on Mars, our passage from the age of spacefaring and into the age of space dwelling will catalyze a fundamental shift, not only in the way that we live, but also in the way that we perceive ourselves in relation to life in this world and elsewhere. Whereas, to a large degree, our rise into a technologically advanced species has been defined as a force for the destruction of life. Our rise into a multiplanetary species will constitute the beginning of a new role for humanity as protectors and stewards of life. Our planet's biosphere has been devastated multiple times in the past. Previous extinction events resulted in the destruction of up to 96% of all species on Earth. It might be scary and unpleasant to think about, but every once in a while, this planet is subject to a massive catastrophe. And there are numerous future threats, not only to us, but all life as we know it. Some of these threats come from human activity, such as unintended consequences of biotechnology and the development of bioweaponry, strong artificial intelligence, and this doesn't mean Terminator robots in the streets. If you're unfamiliar with the problem of AI and existential risk, look up philosopher Nick Bostrom's paperclip maximizer thought experiment. These threats also include, of course, human-caused climate change or nuclear war. And if you're wondering how threatening nuclear war actually is to life on Earth, look up the story of former Soviet Colonel Stanislav Petrov. We literally avoided nuclear annihilation based on a snap judgment by a single individual less than 40 years ago. Finally, These threats might include runaway technology such as nanotechnology. And if anybody wants to learn more about these possible threats, I would encourage you to check out the Future of Life Institute. Now, you may be thinking, well, this kind of sounds like the same old ugly story. To be sure, as always, not all of us will act in the best interest of life on this planet. All the more reason for those of us that are willing and able to pursue the more noble path. And let's not forget, threats to life on this world don't just come from humans. In fact, most mass extinction events on Earth so far have had nothing to do with human activity. There are various natural threats to life on Earth, such as asteroid impacts, bearing in mind that every century there's about a 1% chance of an asteroid hitting Earth that would generate a crater the size of a country. That might sound like a small probability, but on the timescale of a planet, it happens quite frequently. There's also cosmic threats, such as gamma ray bursts or solar superstorms, which, by the way, happen about once or twice a century. One barely missed us in 2012, and if one were to hit us today, it would knock out the world's power grid. There's also major volcanic events, such as the famous Yellowstone supervolcano, and there's natural shifts in Earth's climate. Finally, there's the eventual death of our sun. This is all to point out that living on one planet is extremely risky. Further, recall my earlier discussion of the fact that life might exist only on this planet, or that it might be so rare that Earth is an island of life, separated by insurmountably vast distances in time and space from other such islands. Setting aside those important possibilities, consider that even if our galaxy is teeming with life, the only species from this biosphere, the biosphere that raised us, with the ability to travel beyond the atmosphere is humanity. The only ticket off this beautiful, precious lifeboat is us. And without us, sooner or later, our biosphere will be devastated once again. The implications of this sobering reality for our story are immense. There's no way around the simple fact. Ultimately, sooner or later, most life on Earth is doomed without human intervention. We need to learn how to properly take care of this planet. But our duty to safeguard life reaches far beyond this planet alone. Becoming a multiplanetary species and bringing life and the light of consciousness with us is therefore a profound responsibility that only we can fulfill. But it is also a profound opportunity to change the narrative about what it means to be human. By establishing a permanent presence on Mars, the second most habitable planet in our solar system, we will be providing substantially greater security for not only human life, but for life from Earth, generally speaking. We cannot survive without our fellow Earthlings, and so, by necessity, we will bring them beyond the atmosphere with us. The flora and fauna that are essential to our existence on Earth will be just as important to our settlements on the Red Planet. This will not constitute an escape from Earth, but rather the proliferation of life from our planet to a new home and the establishment of a multiplanetary biosphere that spans both Earth and Mars. It is in the adoption of this pivotal role, which the universe has entrusted to us humble hominids, that our story will be redefined. Humans, the stewards of life. Going to Mars won't just provide a crucial redundancy for life. The technologies that we develop by learning to live on Mars will also have a significant impact on our ability to take better care of life on Earth. By necessity, human life on the Red Planet will be a powerful catalyst for developments in areas such as efficient energy and water use, compact, high-efficiency agriculture, leaner, more efficient construction methods, and recycling and waste management, just to name a few. By learning to live on Mars, we will also be learning to shrink our ecological footprint on Earth. It isn't about choosing a different planet. It's about learning to live wisely and responsibly on both. And if you want to learn more about how technology developed for space helps us live better on Earth, take a look at a publication called NASA Spinoff. It details the multitude of ways in which space technology is put to good use within our atmosphere. And while you're doing that, keep in mind that the task of Mars settlement is an initiative in space greater than anything that we've ever attempted. And so the resulting technologies and innovations will be vastly greater in scope and scale than anything we've seen yet. Eventually, as our technologies continue to advance over the centuries, we will become proficient at traveling to and living on Mars. We may or may not choose to terraform, but either way, more and more life from Earth will join us. Our skill as a space-dwelling species will carry over as a general aptitude for settling other worlds too. Ultimately, as we reach out further and further from the nest, bringing plant and animal, insect and microbial earthlings along with us, the story of humanity will become very different from what it is now. Pause to consider this for a moment. In time, by going to Mars and learning to become multiplanetary, the story of humanity will be the story of a collection of ape descendants who, though they once caused great harm to their home world, would one day carry the seeds of life to entirely new beginnings. What a journey that will be. What a profound and humbling purpose we have before us. This story, our story to come, should stir us into action. This should excite us, should drive us to be better, and should prompt us to realize the potential that we have as a people. Not only to be better caretakers of this world, but one day to become stewards and gardeners of life in this solar system and beyond. Now, not only will going to Mars result in this fundamental inflection point in our story with regards to our relationship with life on Earth, but it will also open up entirely new ways for our story to grow and change. Not long after we first establish a permanent presence on Mars, and as it becomes increasingly safe and comfortable, some of us will decide to stay and even have children. Settlers to the red planet will begin to diverge from their parent civilization in interesting and meaningful ways. In order to communicate in a manner which best reflects that unique environment, a dialect will begin to form. Distinctive traditions of Martian art, music, and literature will take root. The crops that grow well and taste good in reduced gravity will form the basis of new styles of cuisine. Martians will find unique ways of having fun and establish new hobbies, sports, and recreation. Novel Martian perspectives and modes of thought will augment our pursuit of science, philosophy, and religious truth. Mars is going to have its own Einsteins and Marie Curies, its own Louis Armstrongs and Agatha Christie's. And as the centuries turn into millennia and our foothold on Mars enables us to settle other worlds, it will generate an abundance of human thought, expression, culture, and tradition. Our story will, in fact, branch out into a multitude of different stories, ever increasingly dynamic and enriched. Now, I know that this version of our story isn't guaranteed, but it's entirely up to us whether we choose that path or not. And there's good reason for pursuing this narrative. It would provide tremendous benefit, not only in the future, but also today. Though it might take us centuries to proliferate life beyond this planet, by starting to write that story now, we can set an important precedent for our descendants. By taking on the monumental and monumentally important task of Mars settlement, we can reinforce a sense of hopefulness and pride in being human. Children born into a world in which humans live and work on Mars will know a humanity that has made a commitment to reach for new and bold beginnings. True, they will inherit the burdens of our remaining social and ecological problems, but so too will they inherit a project of such audacity and optimism that they can see beyond those problems to a broader and brighter future. They will look to the stars, knowing that our collective journey is boundless, and they will be driven by the excitement and anticipation of what comes next in the story of humanity. Thank you so much for your time. I hope you found this interesting, and I'd love to answer any questions.
Great presentation, Evan. Very
Thank you.
insightful.
Thanks.
Thank you. Thank you. So we have a question from Nina. They say, Evan, I love your speech and so agree with what you're saying. Great plan. But shouldn't we preserve the life of animals and perhaps plants we harvest?
Yeah, I mean, we should definitely preserve. I mean, I think this overall goal will be a way of preserving life far beyond that. So I'm not, could you ask the question? I'm not sure that we harvest plants and animals that we harvest. Could you repeat the question?
Yeah, I can repeat the question, but I'm also just, I'm assuming that the person is also asking about preserving the life of animals and plants here on Earth. That's what I'm thinking the question is, but I'm not sure. So the question is again, but shouldn't we preserve the life of animals and perhaps plants we harvest? Again, I'm thinking that's referring to Earth.
Yeah, for sure. We should preserve life on Earth. And, you know, there's so frequently this idea that we have to choose between taking better care of Earth and going to Mars, but it's not at all the case. You know, those are not mutually exclusive projects. We can do both at once. And as mentioned in the talk, the things that we learn, the technologies and processes that we learn by going to Mars are going to help us do that on Earth. So yeah, for sure, we should do that. And I think this project will help with that. Thanks for the question.
Thank you. Next question is from Melody. Hey, Evan, thanks for the speech. It was such a positive message. Just thinking from the other side, do you see the potential of interplanetary wars and how do you think that would play out?
Yeah, thanks for your question. Well, I guess I would say, first of all, I hope that doesn't happen. Of course, you know, I hope that our transition into space is going to leave that stuff behind. But I would also say that even if that does happen, it doesn't detract from the overall goal of that mission. You know, getting out into space, giving redundancy for life, it's opening the door to a longer future, you know, where I believe that we're steadily on the path towards being wiser as a species, generally speaking. So if we can just keep the door open to the future longer, I think eventually I hope, and I think eventually we will move beyond wars. So if it did come to be that there was some conflict in space, I don't think that would constitute this idea of like, oh no, like it didn't work. I think it would just be like, okay, like the human condition is obviously still present, but we're extending out the time scale of that to give us time to become what we could be one day, which is hopefully not fighting wars. I hope that answers the question.
Thanks a lot. And as we're waiting for more questions, let me ask you one. And this will be a question on this duality or the narrative behind the word artificial. I think when you mentioned the two narratives about humans, or kind of like humans evolving from spacefaring civilization to space dwelling, where do you think, or how do you think the idea of what's artificial or created by humans and natural will change? Because as now we know everything, you know, from the narrative of humanity kind of killing the earth, everything artificial seems to have this negative weight attached to it. But as we're moving toward Mars and other planets, how do you think the idea of something being artificial and natural will change?
Sure. Yeah. Great question. Thanks. I think that that will change in the sense that us reaching out to Mars, I view it as kind of Earth being an organism, a collection of organisms. Like if you look at the human body, we're a collection of smaller organisms, right? And I see humans moving out to Mars as just being sort of the Earth as an organism, providing security and reaching for survival. So in terms of this, this idea of humans being separate from nature or being some artificial imposition onto nature, I think that going to Mars could change that as well, for sure, because it's like we are the Earth reaching out to ensure its own survival. Yeah. Does that answer the question?
Yeah, absolutely. This is also a very interesting perspective. And if I might just add very quickly, I think I've heard somebody mentioning on a very similar note to us being the same organism with the Earth, also kind of like the satellites and everything we use in order to look at the stars as creating this artificial eye for the Earth, so that the Earth is suddenly now able to see what's happening outside. And just this very idea of having humanity being this enabler of kind of a new organ for Earth is very exciting.
Absolutely. I'm forgetting where this quote is from. Sorry about that, but we are a way for the universe to know itself. So I think we are very much a part of the natural process of life expanding and going beyond the atmosphere.
Thank you. And we have a question from Robert Zubrin, who
Great.
is saying, what do you think of the slogan, "Together to Mars, then together with Mars"?
Together to Mars, then together with Mars. I love the slogan. Together with Mars. I like the idea of together with Mars, because I think that sometimes there's this idea that humans would be a problem on Mars for potential life there. But I don't think that's the case at all. I think that just as we can be an ally to life on Earth, if there's any life on Mars, I think we can ally ourselves and work in its best interest as well. Does that answer the question? It's an interesting question. I hope I'm doing it justice.
I think it does. But Robert, please feel free to enter your comments in the chat.
Okay. Am I unmuted?
Yes, you are.
Yeah. Well, what I meant was actually that, together to Mars is self-explanatory. And then together with Mars is that now we have two branches of human civilization working together to take on greater challenges together.
Yeah, absolutely. I love that. I love that idea. I believe in it wholly. Our ability to solve any problems in the future is going to be hugely benefited by the dynamism and the added complexity of the human civilization as between two planets. So I love that idea. And thanks, Dr. Zubrin. You are why I'm here. So I'm delighted to get a question from you.
Well, I'm glad you're here too. So I think you're doing a great job with your articles.
Thank you so much.
Okay.
Wonderful. Thank you very much, Evan, for the presentation and for answering all of our questions.
My pleasure.
So we got a couple of minutes, about 1 minute left. So if the next speaker is ready, then I would be happy to introduce you. But if not, we can probably take a 1 minute, very, very short break. So Vandi, please let me know if you are able to start a little bit earlier.
Yeah, I can start a bit earlier. I wanted to make sure that maybe we can just quickly check if the screen shows up properly.
Absolutely. Yeah, let's do that first. And I would be happy to introduce you. So maybe as you're setting the screen, let me introduce you. So the next speaker is Vandi Verma, a chief engineer at NASA JPL rover robotics operations. And Vandi will be talking about driving curiosity and perseverance.
So let me share this screen. I will try to share PowerPoint and see how that goes. Are you seeing the main screen or are you seeing it as a split screen?
No, we see the main screen. It looks good.
Okay, great. Yeah, thank you for the introduction. So today I was going to talk about Mars 2020 robotic operations and touch upon some of the adventures of operating the first rover and helicopter on Mars. So starting out, I was just going to cover what Perseverance robotic operations covers. And so it involves all of the mobility and navigation. So that's all the driving that we do to get to the different science locations and everything that's done with the robotic arm. So the main purpose of the robotic arm and why we send a rover is because we want to take measurements in situ, really close proximity observations on the surface. And we deploy the tools and instruments at the end of the robotic arm. There's a turret, a 45-kilogram turret, which really carries a lot of the payload. And we can deploy instruments within centimeters of the surface. But it also does a lot of other things like docking with the body of the rover to exchange the bits, which you're seeing in the bottom right image, because inside the rover, the bit carousel that it's docking with has an entire robotic system inside the rover that it is able to put the tubes in and interact with, and also doing things like taking the self-portrait. And the sampling, which I was touching upon, covers the aspects which are, of course, the coring, because the purpose of the mission is to cache sample cores in a large way, and to also, abrade rocks, because Mars is a dusty place, and a lot of the instruments are very sensitive, and we want to blow away the dust from this. So we abrade it, and we also have a gas dust removal tool that can blow away dust from it and study them. And so that's a lot of the sampling system. And then there's the helicopter, which is the Mars helicopter, of course. Ingenuity is also part of the robotic operations. So where are Perseverance and Ingenuity right now? And this image here is an orbital image showing the path of the rover and helicopter. So we've driven 2,600 kilometers, and the white path is Perseverance's path. The blue dot shows where Perseverance is right now. And this is from Sol 210, and we were just in Mars conjunction. And so, today is Sol 233, and we're still at that same location, and we'll be starting operations again tomorrow. And the robotic arm and sampling, we've sent over 20,000 commands. And at all of the locations where you see the stops, the white dots, we will often deploy the robotic arm and take images with the imager at the end of the robotic arm, the Watson camera, or pixel Sherlock observations. And the two locations where we have cached samples is shown in red. So the first one at the bottom, the southernmost one, is Rubion, where we took an atmospheric sample, and the one at Citadel is the Rochette location, where we cached 2 rock sample cores. And we've done 13 flights, which have covered over 2,300 meters. And the green path is showing Ingenuity's path. And the orange dot, keeping with the colors, is where Ingenuity is right now. And Ingenuity also, after conjunction, which was a very big milestone, because it was a technology demonstration, and for it to survive for so long is really quite a feat. And so it is also healthy and doing well. And the number of samples, as I mentioned, we cached is 3. So this kind of gives an overview snapshot of the mission. But going back to what we've done in these last 7 months, so Perseverance landed on February 18th of 2021, as many of you are probably familiar. And a location we've headed to is Jezero Crater. And the reason is because it's an ancient river delta, and the chances that it preserves signs of ancient life are very high. And that's, me at the middle left, holding my lucky peanuts, because if you're doing robotic operations, there's a few things, that are important, but in general, sort of our entry, descent, landing team is really taking us down there. And as you can see, we're very excited. And this picture in the middle is a picture. For the first time, we had pictures during entry, descent, and landing taken by the cameras. And it was really exciting. This was one of the first images. We, of course, saw the HazCam before that. For us to see, the mobility system had deployed, everything looked great. And to actually see the rover in the process of landing, because we actually, during the last phase of the EDL, deployed the suspension, and the rover lands on its wheels. And on the bottom right, I just wanted to give it, this is an artist's conception, but it gives you a sense of the scale of the delta. There's the rover there, and you can see it's a very large formation, even though when we are looking at the orbital images, sometimes you can miss the scale of these things. Here is a graph that shows all of the sols in which we have conducted Perseverance robotic operations. And so right from sol 0, we started doing operations, and we really interleave them. Even though we've had 13 flights, we actually communicate with the helicopter a lot. We transfer data, we do other health checks, so there's a lot of communication. And the mobility really is science-driven. Do we want to get to the next target? Do we want to bump a little bit more because we see something interesting just past where we are at? And so it's driven a lot by that. Of course, as we start driving to the delta, that becomes the primary motivator, and it's driven by mobility to try to get to a particular location. And then the robotic arm, we deployed quite frequently to do various observations. Some of them are planned. We're trying to get to a specific spot that the science team has been thinking about for a really long time. They've looked at it with distant measurements, with remote science, and we're driving up to it. And some of them are just opportunistic. We happen to see in the workspace image, we always take at the end of a drive something really interesting, and so we deploy the arm and took measurement on it. And then the sampling, again, covers the brazen GGRT. And of course, this is all covering a lot of what we've done in this mission is also checkouts so far. So this phase in the early part of the mission is a lot of commissioning as well. So in terms of how we command the rover, just Mars, it looks so much like Earth, so familiar, but it's really, really quite far away. And it can take, depending on the relative position of Earth and Mars, it can take up to 24 minutes just for a one-way lifetime signal to get to Mars. And if we were, from, as we're commanding, if we send them through the deep space network to the rover, we directly command the rover and it receives the commands through the high-gain antenna. If you were to send that, and then the rover takes a lot of data and images and transmits it to orbiters around Mars, and then we get that back through the deep space network. If we did that one step at a time, it would be quite slow. So we don't actually command the rover that way, as most of you know. We actually send the entire SOL's activities, and this could be one or more SOLs, to the rover. But the missions we do are really discovery driven. We're really interested in science input. So as we're making discoveries, science, the more frequently the scientists can interact with it, the more they can update it. Of course, if you're just driving, that doesn't change as much and you want to optimize it. So that's some of how we do our operations. This shows the commands we have sent to the spacecraft every sol. So as you can see, we're sending hundreds of commands. And in the case of sampling, over 1,000 commands to the spacecraft in order to do the operations. Now, this is showing spacecraft commands. Our sampling operations have a lot of abstraction, and we have configurable scripts that do the low-level commands. I'm not showing that, so it would be even a lot more commands. You can just see the magnitude of the commanding depending on what we're doing. So it leads robotic operations really very well to autonomy, because when you're operating autonomously, the spacecraft can make some of its own decisions, and also to abstraction. So here I'm just showing an example of one of the tools. We use dozens of different tools to look at the data in different ways and to make the decisions, so we are sort of cognizant of what is available. Now, not everything we want is available at all times, because we have different bandwidth from Mars. Depends on, sometimes we get a lot of data, and sometimes limited data depending on the orbiter passes. Here's an example of how we plan one of our AutoNav drives, which is autonomous navigations. And we do it in this abstract way. We're sketching the drives. There are things that autonomous navigation with the cameras on board doesn't detect very well, such as sand. And you've seen those red geometric zones we draw, which just said, keep away from this, and various other very abstract commanding that we do. And this translates to those commands. So when we're operating, we're not actually thinking about hundreds of commands on a daily basis, but we have the ability strategically to change them, because we've been on Mars for so long, decades, And we've seen that Mars will surprise you. We've been in so many different areas, and yet we continuously find new things we hadn't encountered before. And you want to have that configurability to be able to change things as needed, but you don't want to think about it on a daily basis. So we do that a lot. And this is the surface transition. So when we landed, you'll see, some of the operations we did right away. The top left is showing the first robotic arm unstow, which was actually the first robotic activity, which was an unstow. And I was fortunate enough to be on that day. And, you're seeing just the arm unstowing, but there's a lot going on in the background, like some of the software that I've been involved with writing, like doing collisions, there were hundreds of those being done. So a lot of things are being checked out. We test very thoroughly, but Mars is a third of the gravity. And there are things we just don't test as accurately. We have really good simulations and models, but the first time is very important. And the middle, you're seeing us, checking out our steering wheel, because we land on our wheels. We want to make sure the mobility system works. In fact, we check all of our actuators. We have, 34 actuators on the vehicle, which are just controlled by the rover's motor control assembly. There are additional actuators on the instruments, such as covers. And in fact, Pixel has a hexapod, because when you position it with the surface overnight, the arm can contract because it's so massive, and it can automatically track the surface to make sure it stays on the target it's observing. And then on the right top, you're seeing the very first drive we did. This was a very important moment, because it meant that, we actually have a rover that can move from place to place. And you see at the bottom left, there are some one-time deployments we do. One is the mast. So we deploy the mast right after we land so we can start taking images. And here you're seeing us, the belly pan was covered with protecting the sample caching mechanism. So we deployed it, then we drove a short distance. And the helicopter Ingenuity was also covered with a debris shield. And we deployed that. And here you're seeing Ingenuity sideways trapped under the rover. And all of these images, the ones that you're seeing under the rover, are taken by taking the robotic arm, positioning the Watson camera under the rover, and taking this imagery. So whenever you look at an image, I always think about, like, how did we take this image? And that's often interesting operations in itself. In the bottom middle, you're seeing us touching the surface for the first time. And you're also seeing the images of the Watson camera where we do refinements, where we iteratively get closer. And we actually use the Watson camera's focus mechanism to tell us more accurately than the robotic arm positioning certainty, how close the surface is if we can't touch it. Touching it, of course, gives us a lot of accuracy. And then on the bottom right, you're seeing us, opening the bit carousel door and starting to really check out the sample mechanism. And then, this mission was special in a way, because we had a second robotic spacecraft along, which was the Mars helicopter. It's a technology demonstration. And it was a 30-day technology demonstration to demonstrate the first powered flight. So right as we landed, we knew where we were. Right away, we started looking for where the most interesting airfield would be to deploy the helicopter. There were some requirements. It had to be flat. It had to be, have very few hazards. And we had certain very precisely defined criteria for that. And also have enough features, so that the helicopter's navigation cameras can actually track them. We also had imagery from the rover. So we started looking at areas that were very close. We also looked at a site that was further along. But if the site closer worked, we would have much more detailed information from the rover's own imagery. And as it happened, slowly as we were working through all the criteria, we had, a lot of meetings. We were analyzing a lot of this data, realized that the site does meet the requirements. And what was then left was to figure out precisely where we wanted to position the airfield, and then rotate the whole flight zone around it. And then another important aspect was the rover was going to observe these flights. All of the images and video you see of Ingenuity flying were taken by the rover. And that's another really interesting operational challenge, because the flights in the beginning, they're on the order of a minute to 90 seconds max. And you're trying to time that very precisely with all the uncertainty that comes from robotic mechanisms with a camera, and also, the frame rate, and you're trying to optimize the rate at which it's collecting data around the most important part of these flights. And this is another image showing this drive that we were doing. We did multiple drives. We approached it from the south, and you're seeing a drive as we're skirting along, coming down towards it. And this is on the right, you're seeing imagery we had taken. So when we went off to deploy the debris shield and we were doing some of the checkouts, we actually drove past the airfield because we already knew it had high potential to take close-up imagery so we could actually really carefully analyze all of the rocks in that area. And this is another one of our tools showing in the image as we're driving up. And we can actually visualize all of these tools, although we have a lot of different ones, they all combined into a common framework. And you can, visualize the helicopter and the rover. And at the moment, of course, as we were driving, the helicopter was strapped under the rover. We hadn't deployed it, but we could visualize what it would be like once we deployed it. And this is a picture. It was a very exciting day when you're seeing, we've actually gone through on the left multiple steps of deploying Ingenuity because, we release one leg at a time. And here it is in the last stage where all of the legs have been deployed, but it's still attached to the rover and just hanging off, centimeters from the surface. And this was a very important drive because we were going to deploy the helicopter. Once you fire the French bolt to deploy Ingenuity, it's no longer attached to the rover, which means it was no longer going to be able to charge from the rover. And the sonar panel had to be unshaded. And that had to happen within 25 hours. Otherwise, the Ingenuity mission was at risk. So it was a very important drive. And we went through a lot of checks to make sure that we minimized the complexity of it. So we weren't doing anything unnecessary. At the same time, took away actually some of the safety checks so we wouldn't get false triggers. But at the same time, Perseverance is a Class B mission, which has a categorization of how important it is as a national asset and the science it returns. And Ingenuity was a Class D mission. So we made sure that the rover was always going to be safe at all times, and but maximize the chance that Ingenuity would survive and get to do its first flight. We also had an additional link where after the French bolt had fired, we didn't have enough bandwidth to Mars that we could actually send another plan in case that hadn't worked. But we had what we call a direct to Earth link where we would be able to get some small amount of telemetry. So we could tell based on our analysis if the autonomous detection on board had been accurate. And if not, we could actually deactivate the drive sequence. And we had one more chance the next morning to drive off. So there were a lot of things we put in place that you have to think about when you're trying to coordinate two missions. And that is the image on the right showing it was a very exciting day, seeing us having succeeded the drive and Ingenuity having been deployed. And then this is an image of the first self-portrait we took where Perseverance took this image with the helicopter. And this is a really neat image because nominally in the mission, after the deployment, Ingenuity was going to drive, Perseverance was going to drive off, and we would never again nominally be so close to the helicopter again. And this was a development, done at a very quick clip, and it's very actually much more difficult to take a self-portrait on the Perseverance rover because the turret is so large and the bit carousel is there. There's actually a lot more probability of colliding with the rover's body. You don't see the arm in the image, which is what is taking this entire selfie. It's composed of 62 frames taken by the Watson camera. And that was, again, operating that. It takes 1 hour of robotic arm motion. And here I'm just showing stills we took. So while we were taking the Watson image, we actually also commanded in parallel to take images from the mast, looking at the Watson camera, taking the selfie images so that we could create this frame of seeing, the arm moving for this process. And towards the end of this movie, you'll see the Watson camera's cover close. And these, this is composed of a little over 150 frames. So it's just stills. And so that's why you don't see a continuous arm motion, but you can see some more details on the details of what it takes to actually compose this image and all of the arm motion involved in creating the image you saw on the previous page. And then here, prime part of the mission really is the science. We're there to study the geology, the astrobiology, and find signs of ancient life, which we're doing by caching these sample tubes. And then, also prepare for humans. And there you're seeing, the sample cubes at the Space Center, or Kennedy Space Center before launch, with very stringent cleanliness requirements being installed. And then once we've done the flights, and I haven't gone into, because I know Teddy talked to and went into all the details of all of the flights and all that we were able to do with that, is to really get to the delta, to accomplish the rest of the science mission. And here we're starting to look at some notional paths going counterclockwise and clockwise to get to the delta. And for this, what's really very valuable is autonomous navigation, because we want to cover distance, and we can only see a certain distance from the horizon, because there's occlusions and there's a view shed. We do a lot of autonomous driving, and autonomous driving really allows us to cover a significant amount of distance. And here I'm showing an image of a checkout of the autonomous capability where you're seeing it swerve around that obstacle. And these images on the bottom are showing the left and right camera images of the actual images that AutoNav used to take a picture of the terrain, analyze what the hazards were, and find a path in it. Perseverance autonomous navigation also has to think about, when we're driving, you also have to think about other factors, such as a helicopter. And here you look at a drive where we are driving right past Ingenuity, and we want to keep a safe distance as we are even autonomously driving, so that we put a keep out zone around it. Although the hazard detection could detect it, we want to maximize that the rover doesn't get close to it. The Perseverance AutoNav is almost 10 times faster than Curiosity. We actually have a dedicated processor on board. It's also a RAD 750 because there are requirements for the robustness and reliability. But it is a dedicated processor that does the stereo processing, and so it can do. And we also have an FPGA that does the stereo image processing. We could do it so fast that as the wheels are turning, we call it thinking while driving, that we can do the image processing, think about whether the terrain is hazardous while we're still turning the wheel. So it really doesn't slow us down. And I'm going to show this next graph, which shows the amount of driving we've done. And there's different modes, but shows you how much we've driven autonomously so early in the mission, which is a lot more. There is a certain amount of driving in the beginning before the AutoNav capability was deployed, where we're doing these directed drives. We always use visual odometry because there's so much slip and sand on Mars. It helps us tell where our position is. We use it in conjunction with AutoNav. And there are certain times when we were characterizing whether certain sandy terrain, how AutoNav was performed, because this area of Mars is very new, and we use what we call guarded mode, where we're actually driving based on the direction from ground, but we're actually seeing how AutoNav would have driven. So you can see we're doing a lot of autonomous driving. And it's been very important. This is showing Citadel, which is the location that was very interesting to science. But where we were, we couldn't see that far because we were actually downslope from it in Seta region. And we were also going to have to cross the ridge in a gap, and we would certainly not be able to do that in the time in one drive. But we also wanted to try to do all of this before conjunction, so we would have the data to analyze on Earth. And here you're seeing this drive where we were able to drive along and then turn on AutoNav, and with visual odometry and AutoNav, we are able to make it through that pass and get all of the distance with AutoNav. So it really allows us to do things like this. And here, just a little bit past that ridge, we found a really interesting target, which ended up being the Rochat. And we drilled 2 sample cores and cached them. And this is, again, another location at which we took the selfie. Typically, once we've taken the first selfie, we execute exactly the same command. So the second one is a lot easier because it's much the same commanding. We change the imaging of how we're pointing the mass so that it's looking at, in this case, the helicopter was in close by. We were looking instead at the drill holes. And when we do the sampling, there was a lot of in situ observations that go along with that. Here you're seeing the arm deployed to take imagery. We create an abraded patch. And on the top right, you're seeing pixel instrument and the results that we got from analyzing that abraded patch, and after we had blown away dust from it. But after we drill, very quickly things get filled in with dust after we clear them out. And then with the Sherlock instrument, all of those dots show all of the locations in which we took Sherlock observations. And that actually is a picture of the Rubion drill hole. But again, we image the drill hole after we take it. And in the middle bottom is a picture which is, really very exciting, because that is a cache cam. That's a camera inside the rover's body that shows us sealing the sample tube. And, here on the bottom left, you're seeing the actual sample core. So that is very exciting because it starts us off on really this first leg of the, proposed, the planned sample return mission, where we're going to be at some point launching these samples from the surface of Mars to bring them back to Earth. And they can be studied in all of the laboratories that we have available on Earth. And this image here is the image taken from the Mars Reconnaissance Orbiter. And it shows Perseverance where it is in South Zeta. And you can see, the tracks. I love these images from orbit. You can actually see the tracks of the rover and see all of the locations we were at. So that's where we were at. And we're going to continue on to collect a few more samples before we start on the long drive and do a lot of autonomous driving as we drive along to get to the Delta. So yeah, at this point, if there are any questions, I'd be happy to take questions.
Thank you, Dr. Verma. And there are questions, of course. So let's start with the first one from Dusty. They say, how do you think AI and things like Tesla, FSD, and Dojo will affect the future of robots on Mars?
Actually, it already is. So we actually have a lot of artificial intelligence capability on board Perseverance as well. Some of it we haven't quite used as yet because, we deploy them in stages. But for example, Perseverance, can take an image. And, this is some of it which I worked on Curiosity and we're bringing to Perseverance. We could take a wide angle camera image. In that, as we're driving along, we might miss things. But when it takes the picture, it can look at what's interesting in it based on what scientists on Earth defined as being interesting. And you could change that criteria. You can say, well, I'm interested in rocks of a certain size and shape, of a certain albedo. And it will then find the most interesting such rock, prioritize it, and can point the narrow angle instruments such as the RMI imager and actually zap it with the laser and send the data back to Earth without requiring ground to have saying, hey, I saw an interesting thing, take a measurement. So we do have that capability. We also have capability planned that we'll be putting on board where we are going to be doing onboard planning, where the rover will be taking some measurements and decide, well, actually, it took a lot less energy because we keep margin on to do things, there's extra time. I might add in some opportunistic measurements because that's interesting. Or if something fails to happen, it might then put in other constraints and put in other activities. So there's a lot of that happening. And I think that really is very important, especially for Mars, because as we go even further out beyond Mars, the communications delays are so much that what you can do on board without ground in the loop, because the rover knows more once it started driving, you don't know what it's going to see. That's really going to help with the science return.
Thanks for the answer. Next question is from Nicholas. How long might both missions last? And have you already found problems with the missions that will inform designing the next generation rover?
You're right. These are great questions. So the mission, the nominal time is, 1 Martian year. So that's approximately 2 Earth years in which it's going to, cache and collect these sample cores. And for Ingenuity, really, it's in overtime already because Ingenuity was supposed to last 30 days. And here we are, over 200 cells into the mission. How long it'll last? The first rover I drove on Mars was the Opportunity rover. And a lot of us would say, you stop betting against these rovers beyond a certain point. And I would love to see Ingenuity come all the way with us to the Delta, following along with the rover and scouting. So, I think if past missions are any sign, it could be a long time, but I will let the rovers decide.
Wonderful.
And actually, the second part of the question, sorry, I forgot about that, whether we've seen issues. It's been kind of really interesting. Of course, we see issues right after launch. There are some interesting characteristics because there's so much going on in parallel. there'll always be some things that are intriguing. They may not cross the bar into being an anomaly, but we have seen things, right? Ingenuity, we've seen this watchdog timer issue, and we updated the software so as not to hit it. We see, other issues with different aspects of it, and every time we see an issue, it absolutely informs the subsequent mission to say, is there something we could do to minimize it? At times you can eliminate it. There are other times where you can do your best to minimize it. And you wonder, we have processes in place. How did this happen? That is a huge aspect of what we think of almost immediately after we encounter the situation. So with Ingenuity, with the watchdog timer issue, it was interesting because we didn't see it in our test rover on Earth. We only saw it on Mars. And so that's another characteristic of saying, what is the difference between the two, and how do you ensure that you can replicate these? But there will always be certain differences between the flight vehicle and the test, even when you build full-scale replicas, and that we always try to, that we will always just see based on statistics, if it's something that happens once in a while, such is the case with a lot of race conditions and other probabilities. That's why we do a lot of regression testing as well to eliminate those. But all of these inform the subsequent mission. In fact, Perseverance has benefited a lot from the lessons we learned from, the Mir rovers, from Curiosity, and even going back to Sojourner.
Thank you so much, Dr. Verma. There are, again, a lot of questions and comments, but unfortunately we are running out of time. So again, if you do have a little bit of time to answer them via the Q&A panel, via chat, that would be amazing. Otherwise, thank you so much for your time. It was very insightful.
Great, thank you so much. Bye-bye.
Bye. All right, so we're right on time for our next speaker. And our next speaker is Dr. Henrik Hargitay, NASA Ames researcher, and they will be talking about mapping the planet Mars.
Hello, can you see the presentation?
Go ahead and
not
start
yet.
sharing again, Henrik.
Okay. Then I will try.
We see your Microsoft. Okay, now we see your presentation. Looks good.
Okay, thank you. So in this talk, I will speak about mapping Mars, but not the research process, but cartographically, in the sense of making a map, or more precisely, this atlas of Mars. Let me give you some background about me. I'm a planetary cartographer. I participated in 2 MDRS missions in Utah, and you can see me in one of the missions trying to navigate there. And I teach planetary geomorphology at Eötvös University in Budapest. So this first geographic atlas of Mars is an outreach project. It's not a research map, but it's based on research. And it's very important that outreach and research is linked in this way. I think many of us think of a geographic map of Mars as something that should be around, but there is none in the market, and for a reason. Because just a decade ago, we simply had no sufficient data to produce a physical map of Mars. And I realized it about 5 years ago, that it was already possible to make it, because we already had the pieces, but we had to put them together. I also needed some examples of the printed end product, and it was an old school atlas, or many of the school atlases I used when I was a child. Why school atlases? Because this is the first, and therefore I think the fundamental experience with maps for most of us. We learn the concept of an atlas, which is a collection of maps and other types of charts and pictures that explain the spatial relations. Now, how can we apply these designs to Mars? First, let's see what kinds of maps or layers of maps we did have before this atlas was made. And from now, we will build this atlas layer by layer. This first layer is the photomosaic. This is the basis of all geologic maps, and this requires mostly technological expertise. If you want to produce a photomosaic, we will need an orbiting spacecraft and to take images and a lot of image processing. But there is no interpretation of the images. That's very important. You see the details and you see many various details, but you never know if that detail is important or not. The reader is not informed about what they see. On Mars, we know that albedo features that you see here in this map reflect the distribution and thickness of dust or fog in the case of Hellas Basin, which is geologically not really important, and yet it dominates the photographic view of Mars. What we want to show on the map is the interpretation and not the raw data. So the image mosaic in this sense is just raw data. Let's move to the DTM. From a map maker point of view, this topographic layer that show relief is the most important visually. If we use the terrestrial colors, like in this map actually, that will give you a false image of the nature of Mars. Terrestrial maps are designed to represent terrestrial experience of the physical geographic environment we live in, and not the Martian. So blue is for depth because it's always underwater. Green is for plains, the color of grass and forest that we usually see when we are in plain geography. Brown is for rocky mountain slopes, and white is for high mountains because it's the color of snow. None of these matches the colors of Mars. So the first task was to modify the color ramp of the relief map. I wanted to replicate the natural colors of Mars, but also to use a color scheme that's reminiscent of the colors from terrestrial maps. So that's a sort of double task here. Here is the process from grayscale DTM to the colored DTM plus the hue shading. So from grayscale, we color it and we add the hue shading that we automatically make using the DTM. And here is the geologic map, the next layer. Unlike the previous ones, these kind of maps are highly interpretive and require a lot of manual work. It takes about 4 years to produce a single map sheet. The problem here is that, how to put it, this map is actually the opposite of the photomosaic. It's too abstract, it's too symbolic view of the surface, at least for a non-expert reader. So it's made the following way. Geologists use photomosaic and trace the contact lines. These are all the contact lines in this global geologic map. And these define the geologic units that form inside the contact lines. The contact lines separate different patterns seen on the photomosaic, and these patterns reflect differences in either composition or structure or the formative process. So these units represent uniform blocks of rocks. Geologists then categorize these units according to the formative processes, like here the impact units or lowland units, polar volcanic units. And they count the number of craters in each unit, which informs us about their ages. So we can see these are the oldest aged units, and these are the latest, the youngest units on Mars. At the end, we can tell for any point on the surface how old is it and what process formed it. But this is a highly specialized map, like mentioned, and the general public is simply not experienced in reading such a map. Perhaps because there is no geologic map in K-12 education. These maps are made by researchers for researchers. So the next kind of map is the geographic map that we also call physical map. Geographic maps show a very complex view of the surface. These are produced by cartographers and not researchers like geologic maps. And these maps are produced for the general public or for school children. So while geologic maps are used for scientific analysis, geographic maps are used to give you a general overview of the area, combining all kinds of existing knowledge about that region. This is why there are no geographic maps of Mars, because Mars research focuses on scientific map production, geologic map production, and it simply doesn't secure funding for geographic maps, because that would count as non-scientific. However, geographic maps use the same scientific resources as geologic maps, and therefore they can only be produced, that's at least I very much think that these can only be produced by planetary scientists who do know where these kind of information can be found. But scientists are, of course, busy in making more geologic maps. So how this map was born then, that's an interesting story. I worked at NASA a few years ago and I mapped the Hellas region, but I had to come back to Hungary, where I am right now with my family. And here at my university, what we do is mostly limited teaching and outreach projects in planetary science, at least. So this is how I invented this project to make a geographic map of Mars, which is an outreach type of map, using the knowledge I collected when I was at NASA, when I made the geologic maps of Hellas and Tarsis region at NASA Ames. I got financial support from the Europlanet, Central European Hub, last year. So let's go back to the geographic map. The base layer is usually a topographic map, like the topographic map here. This is the topographic map, but colored differently than what I did. So the problem with these all kinds of layers is that you have to make first the base layer is the most important. That's because that's what we see. That's what gives the colors of Mars. So the colors are very important. I will talk about that later. Another problem is that while it's very easy to get the data for Earth layers, like the hydrology, the water polygons in this open source website on the internet, you just download it. But for Mars, there's no such place where you can download this kind of base vector layers. So you have to trace the landforms on a photomosaic and create a global database of each types of features, like deserts or peaks or glaciers, where the glaciers are, or where the ice caps are, or the hydrology or the paleohydrology of Mars, because these all are very important, and these all will be the constituents of the geographic map of Mars. There will be no cities and no roads, no administrative borderlines, but there will be some kind of linear feature. I will show you later how I invented that kind of thing that we need for our eyes to see the lines, but that will be a natural phenomenon. So most of this work, tracing the photomosaics and doing this primary research for mapping the surface features, was done in the last decade for Mars. And it's very interesting to mention that it will be done for Venus in 10 years now, in 10 years time from now. So another problem with collecting these layers is that these thematic layers are very much scattered in the literature. Some are published as supplementary data for research articles, like here you see, this is the location for this data is here. Others are published in research papers, like in tables, like here. And geologic maps, of course, are a very good resource for these kind of layers. I started to collect feature catalogs about 10 years ago when I worked on the Encyclopedia of Planetary Landforms. You can see the table of contents here, a list of entries. And some of these landforms are now found as separate layers in this atlas. Now, once you have all the databases together, you need to assign a symbol to each of them, a type of line, or color, or filler symbol for polygons. So these are grouped according to formative processes, like here, impact landforms, volcanic landforms, tectonic, fluvial, glacial, artificial objects, aeolian landforms. And you see that the symbols are a little bit different from the terrestrial ones, but in all, they imitate the visual appearance of a terrestrial geographic map. Now let's take a closer look at one of these landforms, valleys. Valleys are features, and that's again very important. They're too small to be visible on a global map, either topographic or photomosaic. But they are still extremely important if you want to show the true nature of the landscape. So first you have to make an exploratory survey of on a higher resolution photomosaic, trace the paths of valleys, and then display only these lines, these vectors, on a smaller scale map or global map. And here it is at the global scale. These differently colored lines are the traces of valleys on Mars. And valleys are dry. They have been dry for the last 3 billion years. So they are not rivers. It's not the same as hydrology for Earth, but they are paleo rivers. And of course, the problem is that they are older than the oldest rocks on the surface of Earth. And some of them can even be lava channels. So what color they should be on the map? Here's the base layer, and valleys should appear somewhere here in this map. Now, blue is the traditional color of rivers, but you may instantly recognize them. But these are, like I mentioned, not rivers. These are dry valleys. That's different. Brownish color would be a good choice, but the top of this brownish topographic layer, it wouldn't be very much visible. So the color will be magenta in this case, because it's one of the direct colors in printing, which means that you can use very thin lines and it will still be sharp. The Valley database was one of the earliest catalogs, and they were made by Brian Hynek and his colleagues at the University of Colorado. I added some smaller valleys like these valleys in Jezero crater where Perseverance landed. These are the new discoveries, sort of. And I also added flood terrains, what I call flood terrains, which have not been mapped at this detail before. This is the dotted pattern. And I identified them based on island-like streamlined forms that I mapped a few years ago again. This is an unpublished work. Another thematic layer is the sandy deserts and dune fields, which is taken from this existing GIS database created and updated by Rosalind Hayward and her colleagues at USGS Flagstaff. You can drape this dune layer here over any map, and you probably know that sand on Mars is not orange but yellow, or yellow but black, because it's basaltic sand, like on some of the beaches in Hawaii. So to use the familiar yellow symbol for this region that we are used to from terrestrial maps is misleading, but it still works because we all associate yellow with sand. But still, it's not the representative of the color of sand on Mars. So should it be replaced by a black symbol? I chose this brownish color, but it definitely needs some improvements and at least more work. Another thematic layer is the glacially modified landforms, like here in the dichotomy boundary between the lowlands and the highlands. And these are shown in blue, and the ice caps, the permanent ice caps, which are, again, perhaps this is the only familiar color from Mars because it's white on both Earth and Mars. It's just ice. Both kinds of ice are white. There is an extra layer here that you won't find on terrestrial maps, like the one I was talking about, the linear form that we need, the boundary of volcanic regions, boundary of lava fields or any kind of volcanic material. Because there are no other boundaries on Mars. Natural boundaries would be the coastlines, like on Earth, or artificial boundaries. And there's a topographic boundary, sort of the dichotomy or dichotomy on Mars, which is very much visible without any line because it's quite sharp in places, but it's shown in the base layer, the topographic layer. But the most fundamental difference is not between these areas, but between the volcanic and non-volcanic surfaces. So this is how I justify this special focus on this boundary, like this dotted line. And the other thing is that these contain the youngest surfaces of Mars. This is the youngest part of the Martian surface, the latest resurfaced regions, fresh lava flows in Elysium Planitia. As you can see on the map, this is very smooth terrain. In these regions, you can have volcanic or magmatic heat flowing from the interior to the surface, and therefore these may or might support subsurface life on Mars in the past, or perhaps still in the present, and this makes them very important regions for in situ research or one of the next landing sites. So the landing sites, the symbol for the landing site has a special importance because these are the only objects that connect Mars to humans and Earth. Here on the upper right, you can see the landing site symbol designed from the UK. It was selected in a competition that the British Ordnance Survey organized for its first Mars map. And in my atlas, I used a very simple Wi-Fi symbol. Why Wi-Fi? Because the main purpose of landers is to transmit data from the surface, right? So the point is to show that we have radio transmitters on the surface. The radio wave symbol are black for crash landers and white for successful ones and yellow for active missions. All these maps are organized into 30 pages according to the old Mars chart quadrangle system, the MC quads. So each double spread in the atlas shows one Mars quadrangle. Now let's see the global maps. I made several global views using the traditional two hemisphere projections. There are two standard views. One is this, the albedo map that shows Mars as it's seen from Earth or from a distance. This map is not a photograph. It's a vector map based on many different high resolution photomosaics. I tried to color it with colors that approximate the true colors of Mars. The other standard view is the topographic map and the polar views. Now we have a scientific map here, the geologic map that shows the rock types. I used the color scheme, and that's again an interesting story. It was inspired by an old Soviet era maps, which were designed by Kira Shingaryova. And I worked with her in the past, and it's important because her group at MIGAIC, it's important from cartographer point of view, because so at MIGAIC University in Moscow, that was the first group who designed a cartographic comparative atlas of planets in the solar system and the moon. So this is again a first of these kind of works. And the colors and patterns in my geologic map are taken from this atlas, but the actual data is from the 2014 Tanaka et al. Geologic map. Now here's a historic map from the 19th century. And this map was made by the Italian Giovanni Schiaparelli, who first made a cartographic maps of Mars, not this one, because at that time the standard Mars map were drawings that were as realistic as possible. Now, Schiaparelli was the first who decided to apply or imitate the visual technique of terrestrial geographic maps, like this one, sharp lines and symbolic colors, and the complete nomenclature he invented and we still use today, the place names. So I merged many of his maps that he made at different oppositions, different years, to get this global view, and we projected them to match the other maps, and north should be up and south is down. On this same page, in the lower part, I tried to construct a sort of identity for us planetary cartographers, in that I collected the major figures who contributed to the early mapping of Mars. It turned out that the first drawings of Mars, there were female astronomers, and one of them was the assistant of the famous American astronomer Percival Lowell, and her name is Rexy Leonard. She is here, and you can, this page might serve as a first version of the Planetary Cartographer Hall of Fame. And I really like to continue this work, to discover our past in a way. And finally, the climate conditions of Mars, a temperature map. This is an entirely new work. I used actual measurements plus the climate model by the French scientists Forget and Milour. This theme is again based on the school atlases, where they typically include climate maps and climate diagrams. And since such things didn't exist for Mars, they needed to be constructed again. So I created a global temperature map for summer and winter, like these ones, and climate zone maps and climate diagrams. So the diagrams show the daily highest temperatures and daily lowest temperatures at ground level at 2 meters high, which is different. And I also constructed some cloud maps where I merged daily photographs by the Marcy camera of Mars, photomosaics, and it gave us the cloud patterns which are different for the 4 seasons. So weather is perhaps not as diverse as on Earth, but there are fronts, storms, morning fog that you can see here, afternoon clouds, orographic clouds, wave clouds, the polar hood in the northern part, or the southern part during the winter and after the winter. And there are lots of things, except one, which is very important. There is no rain on Mars. And here's the calendar. There are many geography teams calendars on the market. So the plan is that we will have this Mars Atlas issued for every 2 years, every 1 Mars year, with different maps and different content. And there are 3 different editions so far, all published in 2021, and all for Mars year 36. The first was in Hungary. The second edition is the UK edition, and this is the third one in Turkey, in Turkish language. And the drawings were made by my daughter, so we can call it a family business, this Mars Atlas. And to summarize here, in some types of maps, human decisions play little role. Such maps are albedo maps, photomosaic maps, and DTMs that are already available. This map, however, is the result of many human decisions, like what to include, what color, what symbol to use, how to combine them, and so on. So this is the difference between this geographic map and single layer maps. So finally, let's go step by step through the phases of Atlas production, from this grayscale DTM, adding the color, hill shading, valleys, rills, volcanic lava channels, caves and cones, volcanic cones, troughs and scarps, tectonic features, the highest peaks, linear feature labels, which is again important, the typography here, polygon labels, volcanic region boundaries, the albedo names. There's a separate layer of nomenclature for the albedo, the different albedo features, and the geographic grid, and the marginal content for a map. The same for the albedo map. That's the basis, the albedo mosaic. I traced the different values of different strengths of albedo, and I created this color map and adding the grid and the nomenclature, and it looks like this finally. Thank you for your attention.
Thank you very much, Dr. Hargitay. This is very interesting. And the first question we have is, obviously, when might your atlas be available to the general public?
It's already available. The year 36 edition is available through Etsy. So if you search Google, then you will find a way to purchase this atlas. But in Hungary and in the regions where it was sponsored by Europlanet, we sent it to schools and amateur astronomer clubs. And the plan is that there will be a next edition next Mars year in 2 years' time, and that will be available from the US for the US market.
Wonderful, thank you. And the second question or comment is, do you intend to only keep it as a physical book? It would be really useful to use a Google Earth-like online globe where the user could switch between layers.
You're right, you're absolutely right. So, like I said, the basic idea is school atlases that you must hold in your hands. So that's the old school reading book experiments. But you're right. Well, Mars Track is one of your platforms then, where you can find these layers. Some of the layers that we made are transferred to Mars Track. So these, like the hydrology or paleo valleys, are already there. And yes, Google is not providing vector layers yet. It's a little bit tricky, and so the technology is more complicated than doing physical printed Mars book. But probably by the time school atlases will go full virtual, this atlas will also be available virtually.
Thank you very much. And next question is from Stuart. Great work. Do you consider making an icosahedral project? Buckminster Fuller did one for Earth, which you could cut out and make into a globe.
Yes, we have globes. We have virtual globes, but yes, I made several very tricky projections, and that's the maximum that we will do. That probably in the next edition we will add some exotic projections, but only in printed form.
Wonderful. Thank you. And let me just ask you a very quick question about maybe future plans or plans for future editions. What are the areas or type of areas that are yet to be mapped, or something that you would like to be on the next edition of the Atlas?
That's a very good question. Actually, of course, where the heat is, so the Elysium area is a very interesting one, because this is where you see the volcanic, the latest volcanic activity. So to zoom into that area, that would be, I think, a good idea in the future.
Well, thank you very much, Dr. Hargitay. And time's up. We definitely recommend everybody to take a look at the Atlas, and very excited to see what the next editions would be like. Thank you. All right, so we're right on time for our next speaker. And our next speaker is Jose Hernandez, former NASA astronaut and CEO of Tierra Luna Engineering.
First of all, good afternoon, and let me say thank you, and very happy to be here. The first thing I want to do is I want to share my screen so that you can I can project my presentation and you all can see it. So I'll go ahead and start the slideshow, and hopefully you're able to see it now. First of all, I just want to say a little bit about my background. I'm a former NASA astronaut, and I flew on the space mission STS-128 aboard Space Shuttle Discovery on as the flight engineer. We were the second to last mission for station complete. What that meant is if you look at the building process of a house, the second to last mission is almost like the people bringing in the appliances, the furniture, the inner workings of the house is what we were bringing in. We brought in 7 tons of equipment, utilizing the multi-purpose logistics module Leonardo built by the Italians. And most of that equipment was placed inside of the International Space Station, but some of it was placed outside, including ammonia tank assemblies, some antennas, some cameras, and some cabling for the very last module that was going to be attached. And so we spent 14 days up there doing that work. Now, when they announced the retirement of the space shuttle fleet, the only game in town was going with the Russians on the Proton rocket Soyuz capsule. And it involved a lot of travel to Russia. But since I had 5 kids, I figured, they were reaching their teenage years. So I said, I think I'm going to stay here and leave NASA and just start my own consulting company, which is what I have been doing ever since 2012. So the disclaimer I want to give here, want to make sure that we're very clear, is that the opinions and what I say is definitely not a NASA position. It's basically Jose Hernandez, ex-NASA astronaut position. Nonetheless, I don't think I would say anything controversial that NASA would disagree with. I may make a few subtle, smart remarks, but other than that, I think we're okay. Now, the first thing I want to do is I want to address the elephant in the room, in the sense that NASA is no longer the only game in town when it comes to sending humans to space. And the private sector has become what I consider a major player now. You see these three companies that I have outlined there, Blue Origin, SpaceX, and Virgin Galactic, but there's others coming. Those aren't going to be the only 3 sending humans up to space. And the initial thought is, well, they're catering to the space tourism market. But I don't think they can be sustainable if they just did that. Because if you look at human transportation systems in the past, when passenger airplanes came online. They came online about 1914. And I'll tell you, a ticket from New York to Florida was very expensive, and it was only for the well-to-do who could travel at the beginning. And what kept these airlines afloat was that they had a government contracts with the U.S. Postal Service to deliver airmail. So while they became a little bit more inexpensive with respect to the manufacturing process of buying planes and of that sort, the U.S. government helped them because they were essentially subsidized by providing this airmail service for the U.S. Post Office. Well, here it's a little bit about the same process that's going on. You know, my comment is, I don't think if these companies were solely to cater to space tourism, I don't think they would survive. And as you can see, there's companies like SpaceX and Blue Origin that already have contracts with NASA to help them with certain aspects of space exploration that they're, and I'll talk a little bit more about that later on. But in a sense, NASA is the U.S. Post Office for these companies trying to develop some type of space tourism or some type of presence, long duration presence in space. And so NASA is helping them accomplish that because they're being subsidized, quite frankly, with the work that they're doing for NASA. And so, you know, what I want to mention is that not all of these companies are created equal in the sense that I don't think they all have the same end game in plan. I think each of them have different end games. Some of them certainly going for the tourist business, but I just have to look at the architecture of these rockets, and I could tell you that for example, Blue Origin and SpaceX are looking into going into space and going into deep space probably, and they've already have a contracts, for example, to help NASA develop the lunar lander, those type of things. So their architecture is pretty much rockets, if you see them there, kind of like NASA and the Apollo Artemis program that I'll talk a little bit about, that goes into space. And so their end game is, you know, access to not just low Earth orbit, but probably going into deeper into space. And I think Elon Musk has made no mistake that he wants to go to Mars and the moon. So that's consistent, and their architecture is consistent. But then you look at the Virgin Galactic architecture, where it's a space plane that, you know, it goes up 40, 50,000 feet, it's released, and then it does its suborbital flight. And it's up there for a few minutes, and then it comes down. Well, I don't think that's an architecture that's going to be sustainable if all they're doing is taking up tourists up there for a few minutes at a time. That's not sustainable. But I do tell you that given that architecture that I'm looking at, I think they're looking at developing some type of suborbital intercontinental travel ability. What am I talking about? Well, you know, if you go to from New York to Singapore, you know, it's going to take you 14, 15 hours to get there in a regular plane. You can imagine one of these bad boys taking off from New York, and in about an hour, you're able to see, you're able to land in Singapore. So you greatly cut the amount of time required to do intercontinental travel by doing suborbital flights. And that's what I think Virgin Galactic is going after. So they're all going after different things, but all of them want access to space, and they're accomplishing it. Now, we've been in low Earth orbit for, I would venture to say, about the past 50 years, you know, ever since Apollo's the very last mission, Apollo 17, 1972, when we had the last man be on the surface of the moon, Gene Cernan. We haven't sent humans to the moon since then, and that's almost been 50 years. And so what I'm saying is that that we also have that challenge. The eye on the prize for us right now is not really the moon, it's going to Mars. But how are we going to do that? And I think we first need to take baby steps and be able to solve the problems associated with long duration space travel. And the best way of doing it is in the confines of our home, close to our home. And I'm not saying low Earth orbit, because we've been doing that for the past 30 some odd years kind of thing. I'm thinking more about going to back to the moon. But before you do that, you also got to realize that government entities such as NASA and the European Space Agency, the Russian Space Agency, they don't have unlimited funds to say, okay, well, now we're going to start a new program, but we're going to keep the programs that we have right now. I don't think that's sustainable either. So what I'm suggesting is that the International Space Station is probably going to be retired in the near future. It's either going to be given to a private entity so they could operate it and it doesn't cost NASA or international partners additional funds. And why do that? Well, because they're going to move those resources so that they can start working on the next phase of exploration of space beyond low Earth orbit. And again, before we go to the moon, the best strategy is, before we go to Mars, the best strategy is let's return to the moon, except that this time, we're not gonna go there just to collect rocks and dirt and sand and then come back and analyze. This time, we're gonna go there to establish a long duration outpost that then we can address the technical hurdles that need to be solved before we go on into Mars. So we need to solve those problems, and it's better to solve them in the confines of our home. Now, the one thing I wanted to do is just talk a little bit about the brief history of our return to of us being in the moon, as we're going to return to the moon. And that is, you look at your history books, those of you that aren't old enough, you know that NASA's Apollo program went on from 1968 to 1972. And during that, it sent 9 missions to the moon, and 6 of which resulted in successfully landing on the moon. And that meant that there were 12 individuals who walked the lunar surface during that era. 1972, as I mentioned, Apollo 17 being the last one, Apollo 11 being the first, and of course, Apollo 13 didn't make it because of the problems it had. So the next chapter of lunar exploration is NASA's Artemis program. And again, can't emphasize the fact that what the whole purpose is, we're gonna establish a long duration lunar base so we can develop the technologies in preparation for what it is a much more complex mission, which is send humans to Mars and be able to bring them back safe and sound. And so the moon is going to be our test bed. In short, what we do on the moon, which is only 250,000 miles away, a three-day trip, we must be able to do on Mars, which could be up to 225 million miles away, and it's a 6-month trip. Best case scenario, 6-month trip using current propulsion technology. And so that's why it's important. The moon, if something doesn't work on the moon, it's easier to get back. Something doesn't work on Mars, man, you can't forget something, or something cannot fail that's critical, because you are very, very far away from home. And so that's why the strategy is let's develop that lunar base, and let's test out and develop the technologies needed to go to Mars. Now, what does the Artemis mission look like? Well, it has 2 main components for the Artemis system. The first one starts with Orion, and you see a picture there. And it basically has 3 elements to that. It has a crew module right in the middle. and it can fit 4 to 7 astronauts. Below that, you have what's called the service module. And the service module has the life support system. It also has an engine that gives it propulsion. And then on top of the crew module overlaid is what's called the launch abort system. The launch abort system basically is a system that will be able to extract the crew module at the launch pad in the event of a emergency on the launch pad or shortly after takeoff. It's able to pull it out and take it to safety and then parachute down. It has 3 solid rocket boosters and provides that 40,000 pounds of thrust necessary to extract it out. So that's the Orion system. Then the other part, equally as important, is the space launch system, the SLS system. And if you go from the very top to the very bottom, you'll see that it has a cargo hold that's able to take, I would say, about 40 tons of equipment up into space. It has an exploration upper stage, which gives it some additional thrust as it gets into orbit. And then, of course, the initial thrust is the massive core stage with the engines, and then it's helped out by 2 extended range solid rocket boosters. Extended range as compared to the ones the space shuttle system used to use. And here's a pretty good graphic of what a complete SLS system would look like. And as you can see in the cross section, the core stage consists of 2 tanks of oxygen and hydrogen, and it feeds the engines, and then the 2 side solid rocket boosters that provide the initial thrust for the first couple of minutes or so. And it has a total, the whole system has a total of 10 engines. And it has 4 of those the engines, the main engines that look very similar or are very similar to the space shuttle engines, because they were modified and they give a little bit more thrust to it. And fully weighted down, fully fueled, it weighs more than 6 million pounds. And as I mentioned earlier, it could take up to 40 tons of payload, and getting into space, pretty similar to the space shuttle. It takes a little over 8 minutes to get you up into space. So it's a pretty robust system. You compare it to the Saturn V rocket, it's definitely more powerful than the Saturn V that used to take the astronauts in the Apollo architecture. It's slightly, I think it's only about a foot taller, but it definitely, thrust-wise, is definitely more powerful. And so they're getting this system done. Once you're up in space, you lose that first stage, and the system looks like this. You have another 4 engines. They're RL-10C3 engines that when it gets up there, they fire briefly to put the system Orion in what is called a working orbit, so that it's orbiting around Earth. Once it does that, the astronauts now have the time to reconfigure the spacecraft before they fire the engines again in the exploration upper stage you see pictured there, to leave the Earth orbit and to go on their 3-day mission to the moon. As it starts arriving to the moon, it jettisons the upper stage, and then it starts arriving to the moon. Now here's where things have changed a bit, and quite honestly, I'm not sure, because the requirements keep changing because of, I don't think it's a technical issue. It's more of a political issue. It's more of a timing issue. I know that the original plans for going back to the moon called for the construction and creation of a small station like the International Space Station, but it's called the Lunar Gateway, and it's a pre-stage area, so that when Orion arrives, it's able to dock to the gateway, and waiting for it, there is a lunar lander that's attached also to the gateway. And there's other things attached like supplies, those type of things. So the astronauts would get out of Orion. Some of them would climb into the lunar lander. Some of them would stay in the gateway station orbiting the moon, and they would go down, and it would be a reusable lunar lander is the way they envisioned it, and they wanted to design it. And so all that looked great until the previous administration, I think, made an edict saying that NASA shall send astronauts to the moon by 2024. Well, on that time schedule, there was no way NASA was going to be able to get the gateway and pre-stage it and have it ready for the way to operate it the way I just told you. So what they started to work on is towards a plan where they would take gateway would not be in the critical path. In other words, the first missions would be very similar to how Apollo did it, where it would arrive, it would rotate around the moon, and it will already have a lunar lander with it, and it would then go down and to the moon and then come back without a gateway. My hopes is that things have changed again and that they do have a gateway, but quite honestly, things change so fast at NASA that I don't know what the most recent plan is with respect to gateway, if we're going with gateway or we're not going with gateway. Now, once we get to the moon, what's going to happen? Well, this is very interesting because this is a challenge that the astronauts in the Apollo era didn't face. They only stayed for a few hours and would leave. We want a long duration lunar base there. But there's challenges associated with that because you envision building some type of shelter for the astronauts. And this shelter, you've got to look at how that habitat design is going to be, what materials you're going to use, because you're going to be under a very harsh environment. You're working within the vacuum of space. There's no atmosphere on the moon. There's severe temperature variations between direct sunlight or being cast on the shadow of a structure. You also have to be cognizant of the fact that there's micrometeorite impacts. You have to protect yourself from cosmic radiation. And so it would be impractical for us to say, okay, well, we're just going to take 4-6 feet width cement slabs with us to the moon, because that's too heavy and very impractical to do. Even just the cement bags to take them up there is not practical. So what you want to do is you want to use raw materials on the moon and build from there. You can use regolith material, which is basically crushed rock. And the previous speaker, Dr. Hernick, talked about the fact that there's underground caverns. There's pits that lead to lava tubes, and that may be a natural habitat because it's underground and you're shielded. Other health concerns you have to be aware of is that there's a lot of lunar dust, as astronauts found out when they walked on the moon, that if you ingest into your lungs could be a potential hazard. And then of course you're only at 1/6 the gravity of Earth. So what are the long-term health effects of the reduced gravity environment? We're already learning, past 30 years or so, we've been learning about that on the International Space Station, the US Space Station Lab, and we've been finding ways of mitigating it, like exercise equipment and exercising diligently so that we mitigate the effects of muscular atrophy, the bone density loss, but then you also still have to have the psychological effects of long duration being away from home. So all these things are concerns and that we need to address, and we need to have a plan forward with respect to that. Now, what kind of design concepts are out there? There's, I looked around, there's a lot of design concepts with respect to building habitats on the moon. And one of the things, of course, is location, location, location. As any real estate person will tell you, you got to pick the right location. And of course, one of the concerns is you want to be near natural resources. And one of the resources that's most important is water. And it's been said that they've mapped out quite a bit of craters in the southern pole, where the dark side of the crater seems to contain ice, which may be a nice water source. But in terms of habitats, there's been interesting designs. For example, there's been a design from the European Space Agency where it's a build and fill type of design where you go into a small crater and you put an inflatable structure, and then you fill it up to the top. You put another inflatable structure on top, and you fill it, and you keep doing it until you have a multi-layer habitat system and covered with natural terrain for the shielding part of it. And so that's a pretty interesting approach. Another approach is a manufacturing approach. I call this lunar 3D printing because it's almost similar. You take a thin layer of the regolith and you subject it to focus sunlight, and it's a sintering technique where things tend to bond together in a very thin layer, and then you put some more, and then you build it up. You keep the same process, and you're building it up and building it up until you're able to build interlocking brick structures. You can change the shape of them if you shape it. All these type of things you can do on the moon, but we have to be there to start trying it out and see if that works. And then the thing with this is you probably need about 3 to 4 meter thick brick to shield you from the cosmic radiation if you were to just live on the surface and not go underground. But if you do go underground, you can find underground lava tube structures. And my feeling is that the final habitat is probably going to be a combination of the three I just mentioned to you. In terms of how they're going to build it, they'll probably select a lava tube that's big enough where they can put structures on it, and then maybe do a build and fill kind of thing as well. But I think that's very very plausible that could occur.
5 minutes
You
left.
got 5 minutes left.
Yes, and you see that Dr. Hendrick and others in Arizona have built maps where lunar lava tubes exist, and you could have a natural design solution as well. But again, I think it's going to be overcoming it. Now, developing a self-sustaining ecosystem on the moon, the obstacles are pretty clear. I mentioned about the water source. Oxygen is another thing that you need, another element that you need. And you can, there's studies out there of molten regolith electrolysis that releases oxygen. That's pretty interesting too. We must be able to grow our food and produce our own energy. Solar panels, there's material there to build your own solar panels. So in closing, what I'm saying is that when we succeed on the moon, we can set our sights on Mars because the obstacles are very similar to overcome. The only other thing that we need to develop is advanced propulsion systems, aside from the chemical systems, that will get us to the Mars quicker. And the strategy, do we need fueling stations along the way? And how are we going to protect our astronauts along the way from cosmic radiation? You solve those problems and you're almost ready to go to Mars. So we're pretty excited about the future. And I think this is where I end, and we have enough minutes to address several questions. So happy to take them.
Wonderful. Thank you so much, Mr. Hernandez. We do have a couple of questions. The first one is, how are they going to perform suborbital flights in already polluted lower Earth orbit and orbit? Shouldn't they clean it first?
Well, the beauty about low Earth orbit is that things, for example, you take up a CubeSat and you operate it, and in the orbit that it's in, within about 3 months to 6 months, its progression is gonna bring it closer and closer to Earth, and it eventually burns down. So the low Earth orbit things tend to clean themselves up pretty good. The ones that don't clean themselves up pretty good are satellites that are, 5,000 kilometers away, geostationary satellites. Those guys aren't ever gonna, well, they'll eventually make it back to Earth, but it's gonna be hundreds of thousands of years by the calculations. Those are the ones that we should worry about the most.
Thank you. And there's definitely way more questions that we can answer live, but the last question would be from Miguel. And Miguel is asking, do you consider that international cooperation is needed to reach goals to return to the moon, human exploration, and so on and so forth?
I believe so. Look, anytime a private entity spends $1 on space exploration, that's $1 less Miguel and I have to pay in taxes so that they can give NASA a bigger budget, or another country a bigger budget, in the European Space Agency, Japan, or Russia. So I'm all for private entities exploring space and spending their own money doing so, because we all benefit from it. Now, a lot of people say, having so many problems on Earth, why are we out there in space? Why not solve the problems here on Earth? Well, the money being spent for exploration on space it's being spent in Earth and in good paying jobs. Also, the technologies being developed in space are good for repurposing here on Earth. And that's gonna help us eventually. My hope is that technologies that we work up in space is gonna help us so that we can take better care of our planet with respect to the environment and energy, those type of things that are all an issue here on Earth. By having innovation up in space, we can reapply it here and solve problems, real world problems here on Earth. So that's a great question, Miguel. Thank you.
Wonderful. Thank you so much, Mr. Hernandez.
Thank you.
And so with that, we are moving on to our concluding speaker for the morning plenaries. And our final speaker for today's session, for plenary session, is Elizabeth Turtle, the principal investigator of NASA's Dragonfly mission to Saturn's largest moon, Titan. Dr. Turtle, are you with us? Are you ready to start?
Yes, can you hear me okay?
Yes, we do.
Excellent. I'll share the slides here. And can you confirm that you're seeing the slides?
Yes, we do.
Excellent, thank you. So I'm Zibby Turtle. I'm a planetary scientist at the Johns Hopkins Applied Physics Laboratory, and I'm the principal investigator of the Dragonfly New Frontiers mission to Titan. And I'm really happy to be here today to move a little further out in the solar system and to talk about Titan and Dragonfly and what we're going to do there. As those who have explored Earth and Mars know well, for planetary exploration, the ability to travel through, within, and to interact with the environment is immensely beneficial. And most in situ exploration to date has been in the form of driving, but we're starting to look to the skies of other planets as well, as Ingenuity has demonstrated really beautifully. There are, of course, many benefits to being able to fly rather than to drive. And for Saturn's moon Titan, this is especially true. Titan is a unique moon in that it has a dense atmosphere. It's actually 4 times the density of Earth's atmosphere. And that, combined with the low gravity, which is about 1/7 that of Earth's, make it an ideal place to fly. All other things being equal, it's physically easier to fly on Titan than it is here on Earth. And for that reason, the Dragonfly New Frontiers mission is a rotorcraft lander. So it's technically an X-8 octocopter. It has 4 arms and 4 pairs of rotors. And similar to the Mars rovers, Dragonfly is a single self-contained vehicle that carries its entire payload of science instruments from place to place. Now, at Titan, we don't have the same infrastructure we have at Mars, with orbiters that can serve as relays, etc. So Dragonfly communicates to Earth directly from the surface with the high-gain antenna you can see here, which we have to stow during flight, because unlike most spacecraft, we actually have to consider aerodynamics as well. So of course, the work I'm presenting here reflects the efforts of a very large team of people who have been working incredibly hard and making great progress on our design, the design of the mission, on the technology maturation, etc., despite the complicated conditions that we're all working under during the COVID pandemic, working remotely, as you see here in the picture of our team meeting. But we're all just thrilled to be able to continue to make progress toward exploring Titan. So I'll start by giving an overview of Titan itself, and then I'll talk about what we want to learn there and our plans to explore Titan with Dragonfly. So first of all, why Titan? We don't know how life came to form here on Earth, and we can't go back to study our prebiotic history. It's kind of overprinted by biology. So we looked at places elsewhere in the solar system, of course, to provide pieces of the puzzle. And Titan, in many ways, is most like the early Earth chemically. And so it holds keys to understanding our chemical origins. So Titan is the largest of Saturn's 62 moons. It's shown here with some of its siblings. It stands out because not only is it large, but at visible wavelengths, it's very difficult to see the surface because the atmosphere is very hazy. And this is Titan just for comparison to other bodies in the solar system. So Titan's between Mars and Mercury in size, but its atmosphere is, as I mentioned, denser than Earth. So it's actually the second densest atmosphere of the bodies with solid surfaces in the solar system. Titan's actually the second largest moon in the solar system. It's with a diameter a little over 5,000 kilometers. It's just a bit smaller than Jupiter's Ganymede. The surface temperature out at Saturn's orbit is cold. It's 94 Kelvin, and at these temperatures, the bedrock composition is water ice. And the atmospheric composition, like our Earth's, is actually mostly nitrogen, but the next major constituent is methane. And that's where things get really interesting, and I'll talk about that in a little bit. As I mentioned, the surface pressure is about 1.5 times that here on Earth, or the density is 4 times, the surface pressure is 1.5 times. And then deep underneath the ice shell, there's actually a liquid water ocean, similar to many of the moons in the outer solar system. So the methane in Titan's atmosphere undergoes undergoes photochemistry at the top of the atmosphere, and the molecules recombine to form very complex carbon molecules. And these molecules aggregate as they descend down through the atmosphere into aerosols, and this material falls out onto the surface. So we have this very rich organic material that covers the surface, and the surface of a moon made of water ice means that there's the potential for these organic materials to have mixed with liquid water at the surface. Not most of the time, the surface is frozen solid, but at the sites, for example, of an impact crater, or if there is cryovolcanic activity, there's the opportunity for organics to mix with liquid water, possibly for extended periods of time. And so this is what makes Titan such a unique destination, to understand chemical processes that may be like those that occurred on the early Earth, supporting the development of life. So for those who aren't familiar with Titan, for an icy moon in the outer solar system, its geology is surprisingly familiar, with similar surface processes to those we see on Earth or Mars. And this is a map at infrared wavelengths with enhanced color, made by the Cassini orbiter. Cassini was in orbit around Saturn for 13 years, and it mapped out the surface of Titan at a variety of wavelengths, including radar wavelengths and this near infrared mapping. So Titan doesn't immediately look familiar when one looks at it. There are a few impact craters you can see, but there are not many. And there are these big dark areas near the equator, and there are very large dark areas near the North Pole. And I'll talk a little bit about each of these. So it turns out that these dark areas near Titan's equator are fields of dunes, sand dunes, except on Titan, the sand is made of organic material. We don't actually know how you form organic sand grains. We'd like to find out. But Titan basically has the equatorial region is basically the largest Zen gardens in the solar system with these spectacular longitudinal dunes. And this area wraps almost all the way around the planet. Titan, as I mentioned, does have a few impact craters, but like Earth, it doesn't have very many. And that is mostly due to the fact that there are active processes modifying Titan's surface the same way we have here on Earth. And so they're eroding craters and depositing material in them to the point that the craters become unrecognizable. There are also some tectonic structures you can see, and I should explain, this is a radar image. So the features that are bright here are features that are rough at the wavelength of the radar, which is about 2 centimeters, 2.2 centimeters with Cassini's radar wavelength. So what you're seeing here is these bright areas. These are actually elevated tectonic structures. They're actually fairly eroded because there's so many other processes modifying the surface of Titan. And you can see these dark linear features, which again are the organic sand dunes. There's also the possibility of cryovolcanism. This is one particular example called Sotra Patera, which is almost 2 kilometers deep, right next to this mountain. It's 1.5 kilometers high, and when one looks in the radar and infrared data, one can see features that look like flow features on the surface. So we didn't see anything that was active cryovolcanism with Cassini observations, but there are certainly hints that there may have been cryovolcanic activity in the past. And then Titan also has a hydrologic cycle. So Titan has channels, and in fact, at the North Pole, the areas that you see as dark in the map are these large seas. There are 3 large seas here. Ligeia Mare is 500 kilometers across. And then all these little dark features here on the other side of the North Pole, which is about here, are lakes. And these are lakes and seas of liquid methane. There are rivers of liquid methane, and there are even clouds of methane in the atmosphere. And Cassini saw evidence of methane rainfall a few times during its mission. So Titan actually is a world kind of 2 oceans, in that there are these methane seas on the surface, and then there's a liquid water ocean in its interior. Cassini carried with it a Huygens probe built by the European Space Agency, and it made measurements as it descended down through Titan's atmosphere and sent us back this view of Titan's surface. And of course, the view right next to it is a little more familiar, of our moon, just to give a sense of scale. And what you see are these this gravelly plain with rounded rocks that are probably made of water ice, extending off into the distance. So we know that Titan has the key ingredients necessary to be necessary for life. There's energy in the form of sunlight that drives this very complex and rich photochemistry. There's the organic material that is the result of those chemical processes. This material falls out, covers the surface, where it's had the opportunity to mix with liquid water in the past, or perhaps in the present day, if there's exchange between the surface and Titan's interior liquid water ocean. But there's also a second liquid in the system, which is the methane and the active. It's possible that liquid methane could support the development of an exotic biological system. And on Titan, we can study the chemical processes in the context of a planetary environment that's very much like, the processes that materials are exposed to here on Earth. So Titan offers us the opportunity to look for answers to very fundamental questions. What makes a planet, or in this case a moon, habitable? what are the chemical processes that led to the development of life? And even has life developed elsewhere in our solar system? So of course, we don't think that life as we know it certainly would be terribly happy at 94 Kelvin, but we would be remiss if we didn't make measurements to understand if chemistry did take was able to take the step to biology at some point in Titan's past. So Titan has basically been doing chemistry experiments, prebiotic chemistry experiments for us for tens of millions, hundreds of millions of years. And Cassini has shown us where we want to go on Titan to pick up the results of those chemistry experiments. We know that there are diverse surface materials and environments. There's this wide variety of geologic processes, transporting and modifying materials on the surface and mixing them together. So the challenge became, how do we get instruments to multiple sites to be able to sample materials and measure the compositions of these materials? Very similar to the challenges that the rovers on Mars are surmounting in making these measurements with mobile in situ exploration. But as I mentioned, it's very efficient on Titan to travel using heavier than air flight. And so, so that's exactly what we plan to do. So the Dragonfly mission, actually, we have a cruise stage that will get us from Earth to Titan. And then we have a entry vehicle that protects Dragonfly as we descend down through the atmosphere to Titan's surface. And then there is the lander itself, which, as I mentioned, is an entirely self-contained vehicle. It carries our entire payload from place to place the same way we do on Mars. But with Dragonfly, we can make measurements not only on the surface, but also in flight, doing aerial imaging and atmospheric profiles, for example. I also mentioned we do direct-to-Earth communication. We have the high-gain antenna that allows us to communicate. We take advantage of the fact that the antenna needs to be able to turn to communicate with Earth from the surface, and we mount these two cameras here. These two boxes here at the top of the high-gain antenna are actually cameras, and this will allow us to pan these cameras around to build up panoramic views of the terrain surrounding the lander. Dragonfly is designed like Curiosity and Perseverance. It's designed to use an MMRTG for a power source, and we use this to charge a battery that we use to power flight and our science activities. And what is typically referred to as waste heat is actually a significant element in our thermal design, because this allows us to keep everything inside the lander warm in the cold Titan environment. And just for scale, because we tend to think of drones as fairly small things that we can fly around in the backyard, the Dragonfly lander is about the same size as the Curiosity or Perseverance rover. And so this is a prototype. This is a prototype rotor, and I know you don't know how large I am, how tall I am, but I'm a pretty average human being, maybe a little short for a stormtrooper. Anyway, this is me with one of the rotors. So just to give a sense of the scale of this vehicle, it really kind of gives you a sense also of how much easier physically it is to fly in the Titan environment, that we can fly a Perseverance-sized rover from place to place. So Dragonfly is scheduled to launch in 2027 and to arrive at Titan by 2034. We do direct atmospheric entry. We go straight into Titan, no going into orbit around Saturn or Titan. And Titan's atmosphere is very extended. So at Mars, we're used to talking about the 7 minutes of terror. For Titan, the atmosphere goes up to, well, to over 1,000 kilometers altitude. And so this is a 2-hour descent. So there's a lot more time to kind of stage all those activities that when one is approaching Mars have to all happen in a very short period of time. But at Titan, we have 2 hours for this sequence to take place. We'll actually be landing at a similar latitude and similar time of year of Titan's year as the Huygens probe, and so we know what the atmosphere is like at this time of year in these areas. The initial landing site provides access to a wide variety of materials. We're going to land within the sand dunes, these organic sediments, to make measurements of their composition. The interdune areas between the dunes actually have a water ice component. So within very close proximity, we have two different materials with very different histories. And then the landing ellipse is just south of this impact crater. This is the Selk impact crater. It's about 80 kilometers in diameter. And we will explore this area, which will allow us to study an area where organics may have been able to mix with liquid water impact melt. Another benefit of landing in the interdune areas, these are terrestrial analogs. This is the Namib Desert. It's a very good analog for these longitudinal dunes that we have on Titan. Both of these pictures, though, of course, are taken on Earth. In addition to the fact that there are two different materials on Titan in the sand dunes themselves and the interdune areas, the interdunes form these very wide flat areas, which are ideal for landing as well. So there's a practical reason for landing in this area as well. And then it gives us access to the deposits associated with this impact crater. So Dragonfly exploration is planned for a little over 3 years, or 74 T-sols, 74 Titan days, over which we'll traverse up to 180 kilometers, exploring a couple of dozen unique sites along the way as we go through the dunes and interdunes and then into the deposits associated with the impact crater and possibly down into the impact crater itself. I should say this is a very extended, a very vertically exaggerated profile here. The topography is really only on the order of a few hundred meters, and this is a 200-kilometer, x-axis. So, like most icy satellites, the topography is very subdued. So at Titan, again, we don't have the same infrastructure we have at Mars. We don't have orbiters that can do scouting for us. So Dragonfly will actually scout for itself. We have global maps from Cassini, but those are at a lower resolution scale. And so Dragonfly will actually do what we call a leapfrog. What we call leapfrog flights. And so from a landing site, we'll take off, we'll fly past the previously scouted landing site, that is our target landing site, and go ahead and scout a new area, and then come back to the previously scouted landing site. And so this allows us to look ahead to areas where we want to go, to study, to not only look for hazards and do hazard assessment for safe landing sites, but also to look at the areas that offer the most scientifically. The nominal flight schedule is about once a Titan day. Titan days are 2 weeks long, about 16 Earth days long. So it's about one flight a month, which means that most of the time is actually spent on the surface making science measurements, transmitting data to Earth, etc. And we make multidisciplinary science measurements. The focus, of course, is the prebiotic chemistry, analyzing the composition of the surface materials, but we want to put that in the context of Titan's atmosphere, its methane cycle, the transport and mixing of organic material on the surface, and then the opportunities for the organics to mix with liquid reservoirs, be they liquid methane or liquid water. And then again, we have the capability to search for chemical biosignatures of water or hydrocarbon-based biological processes were they to occur or have occurred. And this is just a reminder for those who are more interested in more information about the science. There's a paper in the Planetary Science Journal that just came out this August by Barnes et al. And this is it summarizes the science that we're doing. So there's a lot more information there if people are interested. Dragonfly will carry with it a mass spectrometer. The DRAMS mass spectrometer built by Goddard is based on heritage from the SAM instrument that's on the surface of Mars right now. We have two drills, rotary percussive drills. This is the Draco system, or the drill for acquisition of complex organics. We use this to break up the surface. We use pneumatic transport to bring the materials into the mass spectrometer. Then we also have a suite of geophysics and meteorological sensors, including a seismometer to listen for Titan quakes, and to monitor the atmospheric conditions. We have a suite of 8 science cameras that look downward and forward, and I mentioned the 2 panorama cameras up here on the high gain antenna. And then we also have a gamma ray neutron spectrometer that'll let us measure the bulk elemental composition for context of the surface area under the lander. So as I mentioned, the team's been really hard at work. We've been doing a lot of testing of hardware in the Titan environment, demonstrating the elements will survive in the Titan environment. And we've also been doing a lot of testing of the guidance algorithms and the control algorithms on some octocopter platforms. So I have a couple of little videos here, which I think I'll show if this works over the Zoom. And so this is one of our autopilot test flights. And what you're seeing on the right is the imaging from the navigation system that will be used to do optical navigation during Dragonfly flights. And another thing we're doing is getting other people involved in the project. We have a guest investigator program that is designed to expand opportunities to participate in missions, to get experience, even in these early stages of the mission, the design and development stages, by bringing in students who don't necessarily have experience or connections to Dragonfly or other missions, or may not even have a planetary science background, but to bring them in to give opportunities to really broaden participation, to build on-ramps and provide networking opportunities so that we can expand the training of a next generation of mission team members and leaders. So there's a lot going on. I know we don't have a lot of time. I will wrap up there, but I'll be happy to take questions as well. Thank you.
Wonderful. Thank you so much, Dr. Turtle. We do have a lot of questions. So let me start with one from Kaj. I understand Dragonfly's ceiling height will be as high as 13,000 feet. Will it make use of its ability to fly higher than the highest mountains of Titan? And if so, for what purpose?
So the mountains are pretty subdued compared to what we think of as mountains. Most of the mountains are only a kilometer or two high. And the area that that we'll be flying in doesn't, besides the crater, there's not a lot of topography in that area. Mostly the reason we want to be able to fly a few kilometers up is to make measurements of the lower part of the atmosphere, to understand the atmospheric behavior. And how it changes with altitude. So we would be able to fly over, a mountain if it were there, but the intent of the altitude profiles are really to understand the atmosphere better.
Thank you. Next question comes from Bernard Foying, and he asks, how far will you be from Huygens landing site? Any chance to investigate what happened to the Huygens lander?
It would be really interesting to go to the Huygens landing site, but it's actually several hundred kilometers away. So that is not part of the mission plan. The intent is to explore a different area of Titan and gain a sense of the diversity of the surface materials. But I agree, it would be really fascinating.
Thank you. Next question is from Doug, and he asks, to date, our best sterilization of Mars landers sent less than 0.1% of Earth microbes. How will Dragonfly be sterilized so we can study prebiotic chemistry and a search for life?
So it's actually, so we do absolutely have to make sure that we know what we would carry with us and make sure we don't carry things with us that we would measure with the instruments. But on Titan, it's a somewhat different environment than Mars in that there is a lot of organic material. So the biggest challenge becomes making sure we're not cross-contaminating, that we don't get from, not that it's a problem for Titan because materials move around on the surface of Titan all the time, but to make sure that when we make compositional measurements at one site, and then make compositional measurements at the next site, that we're not, still measuring materials that were sampled the time before. So that's really what drives our contamination control requirement, is making sure that we're able to, the system stays clean between sampling sites. But absolutely, we need to pay attention to cleanliness all along the way as well, to make sure that what we're measuring on Titan is native to Titan in terms of the chemistry.
Wonderful. Thanks a lot. And as always, we have so many questions, but let me ask you the very last one from Dr. Zubrin. And he asks, what limits the lifetime of Dragonfly?
The lifetime limit is the output from the MMRTG, and not in terms of power so much as in terms of heat. Because as the output from the MMRTG declines, there will be less heat put into the Dragonfly system. So the 3 years allows us to get from our initial landing site to the area around the crater that we want to study. The lifetime limit from the MMRTG is several years. Eventually there will be low enough power output, low enough heat output that Dragonfly won't be able to stay warm anymore. But that's several years, so we actually have a good amount of margin on our nominal mission lifetime.
Wonderful. Thank you so much, Dr. Turtle, for a great
My
presentation.
pleasure.
We're very happy to have you conclude our final day of morning plenaries and segue right into our afternoon sessions, which are about to begin. So I'll hand it over to James for any last-minute announcements or remarks. Otherwise, see you all at the afternoon sessions.
Thank you, Dr. Turtle, and thank you, Lyra, for doing such a great job today with the Q&A and introducing the speakers. You did great. Just one last appeal for those of you who've been enjoying our sessions. This year's conference is free, but we are asking for you to send in a donation. You can use the donate form in Attendify. You can also just go to our website, marssociety.org, and look for the donate link there in the heading of the site. Please give whatever you can to help support our organization and its programs. So that concludes our morning plenaries. We are now going to start our track talks. We have 2 tracks today, and so you can find those in Attendify. Enjoy the rest of the conference.